Everything you've ever loved, every star, every world, every living cell, may have erupted from something that looks disturbingly like nothing. The early universe was almost perfectly smooth, yet today it's carved into galaxies, clusters, and cosmic webs. So what broke the symmetry? What seeded the first structure? And what are we still missing in the story of how emptiness became a universe? The universe keeps its oldest secrets in the coldest light and in the silent gravity we cannot see. Follow those clues far enough, and certainty begins to fray at the edges. In this documentary, we treat the cosmos like a crime scene. Every photon a witness, every spectrum a fingerprint, every map a partial confession. We will move from the nearest stars to the farthest horizons, because distance is also time. As our view recedes, familiar galaxies thin out, then vanish into a deeper darkness that once filled everything. Yet in that darkness, faint patterns persist, subtle, statistical, and stubbornly consistent across the sky. Those patterns are not simply beautiful. They are constraints, and they narrow what the universe could have been. They tell us that structure was not improvised late, but planned early by rules we still debate. Somewhere between the first instance and the first atoms, the universe acquired a preference. An imbalance so slight it barely registers, yet strong enough to build everything. We can measure the aftermath with exquisite precision and still not know the ultimate origin of the first irregularities. So we proceed the only way science can, by reconstructing a history from relics. We will watch the primordial fireball cool into a transparent cosmos, and listen for the moment when light finally traveled freely. We will read the afterglow as a map of pressure, waves, and potentials, preserved like ripples frozen into glass. We will enter the long night before the first stars, when chemistry was sparse and gravity worked patiently in the dark. And we will track how matter gathered along unseen scaffolding, forming filaments, nodes, and the galactic cities that later lit the void. Along the way, we confront the components that dominate cosmic evolution while refusing to show their faces. Dark matter shapes the architecture, yet hides from our detectors. Dark energy drives expansion, yet resists a clear physical explanation. Even the best theories succeed with conditions they do not fully justify, and the best observations end at a luminous wall. That boundary is not failure. It is the frontier where inference replaces imagery, and where the next question begins. Our journey will be guided by instruments that translate the invisible into evidence, from precision microwave telescopes to deep field surveys and gravitational lensing. We will compare competing ideas, follow the tensions in the data, and ask why different methods disagree by just enough to matter. We will see how simulations can grow a cosmic web from tiny seeds, then struggle to predict the messy lives of real galaxies. And we will return again and again to the uneasy gap between what we can describe and what we can explain. Because the mystery is not whether the universe became structured. It did. The mystery is why the first conditions contained the right kind of imperfections, and why the laws allowed them to grow. If the universe began nearly featureless, then every spiral arm, every element heavier than helium, every habitable world is the consequence of a near-perfect balance that was never quite perfect. In the end, we may not find a final cause, but we will discover how far the evidence reaches. and where it still falls silent. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. From the first whisper of the early cosmos to the rise of galaxies and the making of a homeworld, each chapter follows one clue deeper. And at the edge of knowing, we will face the remaining unknowns that keep the universe unfinished. Galaxies fill the sky in every direction, arranged in filaments, walls, and vast voids that seem carved from darkness. On screen, the cosmic web looks almost biological. Threads of light, knots of clusters, and empty basins where few galaxies live. Yet our best evidence points back to a beginning that looks almost featureless, as if the universe started without a blueprint. The central mystery is simple to state and hard to finish because the data are crisp while the cause remains elusive. How does structure arise from an early cosmos that resembles nothing? By nothing, we do not mean absolute emptiness or a blank stage with no physics. We mean a near-uniform, vacuum-like state dominated by energy, with few durable landmarks to distinguish one region from another. We mean missing information about what came before the earliest observable moments, where our equations still run, but our measurements fall silent. We mean a universe that begins in our data, already expanding and already cooling, as if the opening scene has already started. The farther we look, the earlier we see, and the smoother the universe appears at those great distances. Distant galaxies blur into a background, and then into a faint afterglow that wraps the entire sky. That afterglow is the cosmic microwave background, the CMB, our oldest light, now cooled to just a few degrees above absolute zero. It is a snapshot of a young universe that is astonishingly even, almost the same temperature in every direction. It is also a map of tiny imperfections that should not exist in perfect nothing, and those imperfections are where the story begins. Chapter 1 begins with that contradiction because it is the documentary's first hard edge. The universe is structured now, but it was almost smooth then, and that almost carries enormous consequences. If the early cosmos was nearly uniform, what seeded the first clumps that later became galaxies and clusters? If space began in a simple state, why did it not stay simple forever, fading into a thin, quiet uniformity? To orient ourselves, we need a timeline, even if the first pages are torn. We can speak carefully about fractions of a second after the beginning, but we cannot show footage, and we should not pretend otherwise. We infer conditions from physics tested in laboratories, from particle accelerators to atomic clocks, and from patterns written across the sky. We also admit where inference becomes speculation, because the early universe rewards humility as much as it rewards imagination. In the earliest fractions of a second, temperatures and densities were extreme beyond ordinary intuition, so extreme that familiar categories break down. Matter as we know it could not exist as stable atoms, because energetic photons would tear electrons away instantly. Energy, particles, and radiation formed a hot, dense mixture in constant transformation, with collisions happening faster than any chemical process could begin. The universe expanded, and expansion changed everything by thinning and cooling that mixture, turning speed and scale into the first governing parameters. A key idea enters early, and it remains controversial in its details even among experts. Many models propose a brief era of rapid expansion, inflation, that stretches space dramatically in a tiny fraction of a second. Inflation is not a decorative add-on, but a proposed solution to specific puzzles that appear when we take the CMB seriously. It can explain why distant regions look similar despite limited time to communicate, because they were once close enough to share conditions. It can also explain why space looks so flat and why the CMB is so uniform, as if curvature was ironed out by an enormous stretching. Visually, inflation is often drawn as a curve that suddenly shoots upward, a calm line that becomes a vertical surge. That picture is simplified, but it captures the point. Space itself is the thing expanding, not matter flying into emptiness. Quantum fields, which cannot be perfectly still, would have been present even in that smooth state. In inflationary thinking, microscopic quantum fluctuations are stretched to astronomical scales, turning subatomic randomness into a cosmic pattern. The seeds of galaxies may begin as the smallest possible tremor, magnified until it spans millions of light years. But inflation also raises uncomfortable questions about beginnings, and those questions are not cosmetic. What triggered it, what ended it, and what came before it remain open, and different models answer differently. Some versions imply a multiverse, others do not, and none are directly observed in the way a planet or a star is observed. We treat inflation as a leading hypothesis, not a settled origin story, because the early universe is where evidence thins faster than imagination. Even with inflation, uniformity remains a puzzle that must be handled precisely, not poetically. A perfectly uniform universe has no preferred place for matter to gather, because every location is identical to every other. If density were exactly the same everywhere, gravity would have nothing to amplify, and the cosmos would remain a smooth, expanding haze. Structure would never start, and galaxies would never appear, so the fact that galaxies exist is already a measurement. It tells us the early universe contained differences, however small, and those differences had to be coherent enough to grow. Those differences are the first whisper of complexity, and the CMB lets us hear them. In the CMB, they appear as temperature variations at the level of tens of microkelvin, a few parts in 100,000. On a full sky map, those variations look like mottled color, tiny warm and cool patches scattered across a sphere. They correspond to tiny density contrasts, seeds that later become clusters and superclusters, and they preserve a statistical fingerprint of the early universe. They are the earliest measured hints of the cosmic web, and they are also a clue that the universe was never truly nothing. The CMB is not just a photograph, but a physical record of sound waves in the primordial plasma. Before atoms formed, photons and charged particles were tightly coupled, and pressure could push back against gravity. That push and pull created oscillations, like ripples in a drumhead, except the drumhead was the entire universe. When the universe became transparent, those oscillations froze into the pattern we see today. The peaks and troughs in the CMB's statistics are therefore a kind of fossil acoustics, a memory of pressure, gravity, and timing. Gravity is the storyteller that turns whispers into architecture, and it does so with patient inevitability. It does not create matter, but it shapes where matter goes, and it rewards even the slightest imbalance. Where density is slightly higher, gravity pulls more strongly, and the region grows denser still as it gathers material from its surroundings. This feedback is slow at first, then relentless over billions of years, and it acts across scales from small halos to superclusters. From small perturbations, gravity can build the scaffolding for everything else, including the first places where stars will ignite. Yet gravity also competes with pressure and expansion, so growth is never guaranteed. In the early universe, radiation pressure resists collapse, and rapid expansion stretches perturbations apart before they can deepen. The outcome depends on timing, on composition, and on the size of the initial seeds, because different scales enter the horizon at different times. The early universe is not just a hot fog, but a dynamic system with rules that can be calculated. Those rules are written in equations and tested against sky maps, and the match is one of cosmology's great achievements. We can outline the early timeline without pretending to know every detail, and that discipline matters. At around a fraction of a second, the universe cools. Enough for fundamental forces to behave as we recognize them, separating into distinct interactions. Quarks and gluons begin to confine into protons and neutrons as temperatures drop, transitioning from a quark-gluon plasma to bound particles. A few minutes later, the first nuclei form in primordial nucleosynthesis. When the universe is cool enough for nuclear reactions to build light elements, hydrogen and helium dominate, with traces of lithium and little else, and those proportions can be predicted with remarkable precision. There is history behind this confidence, because these ideas were not always obvious. In the mid-20th century, theorists argued that a hot, early universe would leave behind both light element abundances and a cooled relic radiation field. When the CMB was discovered in 1965, it was not just a new signal, but a decisive clue that the universe had once been dense and hot. Later satellites mapped the CMB with increasing precision, revealing the tiny anisotropies that structure formation requires. Each improvement narrowed the space of plausible beginnings, even as it sharpened the remaining mysteries. This early chemistry matters because it limits what can happen later, and it determines how quickly complexity can appear. Without heavy elements, there are no rocky planets and no complex molecules, and even gas cooling in early clouds becomes more difficult. The early universe sets the initial inventory for cosmic evolution, like a pantry stocked almost entirely with hydrogen and helium. It also sets the initial conditions for how gravity will sculpt matter, because composition affects pressure, cooling, and collapse. The first stable ingredients are simple, but their distribution is not perfectly smooth, and that imperfection is everything. Still, we face a boundary we cannot cross with light, and it is a boundary set by physics rather than technology. Before about 380,000 years, the universe is a plasma that scatters photons constantly, because free electrons act like a fog for light. Photons cannot travel freely, so we cannot see earlier directly in electromagnetic waves, no matter how powerful our telescopes become. The CMB marks the moment the universe becomes transparent, when electrons and nuclei combine into neutral atoms in a process called recombination. That surface of last scattering is a wall in our observations, a luminous curtain drawn across the past. Beyond that wall, we rely on indirect traces, and we treat them like forensic evidence. We use the abundances of light elements as a fossil record of early temperatures and expansion rates because nuclear reactions are sensitive to those conditions. We use the statistical pattern of CMB fluctuations as a record of primordial seeds, including their scale dependence and overall amplitude. We use the distribution of galaxies today as a grown-up version of those seeds, evolved by gravity and cosmic expansion. Each line of evidence is powerful, and each has blind spots that must be acknowledged. This is where observational astronomy meets theoretical astrophysics, and where they sometimes clash in productive ways. Observers measure spectra, redshifts, and anisotropies with instruments that have noise, calibration limits, and subtle selection effects. Theorists build models that can be elegant, flexible, and dangerously adjustable if they are not constrained by data. The partnership is essential because neither side can solve the origin alone, and each corrects the other's blind spots. The friction is also essential because it forces models to earn their claims, one parameter and one prediction at a time. Modern surveys map millions of galaxies to trace the cosmic web, and the visuals are both beautiful and unsettling. Points of light become filaments. Filaments converge into dense nodes, and the empty regions widen into voids that feel like missing matter. They reveal a universe that is not random, but patterned on the largest scales, as if gravity has been weaving for billions of years. Filaments connect clusters, and voids open between them like negative space, shaping where galaxies can form and where they cannot. The web is a late-time imprint of early-time fluctuations shaped by gravity, and it is also a test of what the early universe was made of. Because ordinary matter is not enough to build the observed structure on schedule, given the universe's age and the strength of early pressure. The growth of galaxies and clusters appears to require additional gravitating material that does not emit light, so it does not show up in ordinary images. Dark matter enters as a working explanation, inferred from motions, gravitational lensing, and structure formation across cosmic time. It behaves like a silent framework that helps gravity act earlier and more efficiently, allowing clumps to grow while ordinary matter is still coupled to radiation. Its nature remains unknown, and its absence from laboratories keeps the mystery alive, even as its gravitational fingerprints accumulate. Dark energy, the driver of accelerated expansion, complicates the story further by changing the universe's late-time rhythm. It alters how structures grow over time by stretching space faster at recent epochs, making it harder for gravity to pull matter together across large distances. It is measured through supernovae, the CMB, and large-scale structure, but its physical identity is unclear, and its simplest description may not be the final one. In a documentary about unexplained mysteries, it is a reminder that the universe still hides its main components in plain sight. The problem of nothing is also a problem of unseen something, and our accounting is incomplete. So we return to the opening question with sharper edges and better tools, but not with closure. We have a nearly uniform early universe, a rapid expansion that may set initial conditions, and tiny fluctuations that seed later structure. We have gravity as an amplifier, and we have a cosmic record in relic light and galaxy maps, each acting like a different kind of archive. We also have a hard observational horizon and a prehistory that may never be directly visible, at least not with light. The beginning is close in time, but far in access, and that distance is conceptual as much as it is observational. What we can measure is impressive, but it is not complete, and the incompleteness is part of the plot. We can measure the CMB with exquisite precision, yet we cannot see behind it, and we must infer what set its initial pattern. We can measure element abundances, yet we cannot watch nucleosynthesis happen, and we must reconstruct it from outcomes. We can simulate structure formation, yet we must assume ingredients like dark matter and initial perturbations, then test whether the simulated universe resembles the real one. Every step forward reveals another missing premise, and each missing premise becomes a new question. The early universe, therefore, becomes a disciplined kind of mystery, constrained by data, but open at the edges. It is not a blank canvas, but a puzzle with pieces that fit only certain ways. Even if we do not yet know the picture on the box, the smoothness of the CMB is both a triumph and a provocation, because it confirms a hot beginning and exposes a deeper why. It tells us the universe began in an ordered state, and it dares us to explain why order was there at all. It suggests that nothing in cosmology is never truly nothing, because even the quietest state contains fields, fluctuations, and rules. As we watch these maps and simulations, a thought lingers behind the numbers. If the first seeds were quantum in origin, then the largest structures in the universe may trace back to the smallest uncertainties allowed by nature. If the early universe was almost perfectly smooth, then the existence of every galaxy is evidence of a tiny, ancient asymmetry. And if our observational wall is permanent, then some truths about the beginning may be knowable only through their consequences, not through direct sight. In the chapters ahead, we follow the cooling universe as it gains stable forms. We track how a hot plasma becomes neutral atoms, and then the first stars, and we watch darkness give way to the first sustained light. We watch gravity turn faint statistical ripples into luminous structures, building from invisibly small contrasts to spectacular cosmic architecture. To understand how nothing becomes something, we start where the universe first allows matter to endure, and we keep listening for that first whisper. Chapter 1 ended at a hard observational wall where light could not travel freely. Chapter 2 begins just before that wall, inside a universe still opaque. We are not looking at darkness in the familiar sense. We are looking at a medium so bright and dense that brightness cannot escape. The early cosmos is not empty space with scattered particles. It is a hot plasma, where electrons, protons, and helium nuclei move unbound. Photons are everywhere, not as occasional flashes, but as the dominant population of the universe. In this era, radiation is not merely something matter emits. Radiation is the environment that matter lives inside. Imagine the visuals as a glowing fog with no horizon. Every direction is filled with light, yet no direction reveals a scene. Photons collide constantly with free electrons, and each collision scrambles the photon's path. A beam cannot stay a beam for long. Its information is randomized almost immediately. Light exists, but it cannot carry an image. This trapping is not due to dust or smoke. It is a consequence of charged particles and a simple electromagnetic interaction called Thomson scattering. Free electrons are extremely efficient at deflecting photons at these energies. The mean free path of light, the average distance a photon travels before scattering, is tiny compared with cosmic scales. The universe is therefore optically thick, like the interior of a star, even though it is expanding. Expansion is the engine that changes the rules. As space stretches, the average temperature drops and particle energies fall. Cooling is not a side effect, but the condition that makes stable matter possible. The central question stays in view. How does near-uniform energy become the structured universe that later forms galaxies and worlds? The cooling is subtle in concept and relentless in practice. The universe cools because expansion dilutes energy, and because the wavelengths of photons stretch with space. Each photon loses energy as its wavelength redshifts, and the entire radiation bath slides toward lower frequencies. In plain terms, the universe's light becomes softer over time. In this era, ordinary matter is chemically impossible in the everyday sense. An electron can approach a nucleus, but a high-energy photon can knock it away. The universe behaves like a furnace that refuses to let atoms keep their electrons. Even when a neutral atom briefly forms, it is quickly ionized again by the surrounding radiation field. The result is a charged fog that couples matter and radiation into one fluid. Baryons, meaning protons and neutrons bound into nuclei, cannot move independently of the photon bath. Radiation pressure pushes back against compression, and that pressure is not a minor effect. It is one of the dominant forces shaping what can and cannot grow. The timeline matters because the physics changes quickly as temperature falls. Within minutes, primordial nucleosynthesis has already built light nuclei. The universe is still hot enough for nuclear reactions, yet it is cooling so fast that reaction windows open and close. This is chemistry's ancestor stage, nuclear bookkeeping rather than molecular structure. Protons become hydrogen nuclei, and neutrons mostly end up bound in helium. A tiny fraction forms deuterium and helium-3, and an even smaller trace becomes lithium. After that, nuclear fusion largely stops because the universe thins too fast. Density drops, collisions become rarer, and the nuclear furnace goes out not from lack of fuel, but from lack of contact. A useful way to visualize this is a firework that expands too quickly. The sparks are energetic, but they fly apart before they can combine into anything heavier. The early universe briefly had the temperature for fusion, but it did not have the sustained density that stars later provide. Stars are slow, gravitationally confined reactors. The early universe is a rapid, unconfined flash. This early element inventory is simple and measurable. Roughly 3/4 of baryonic mass is hydrogen, and about 1/4 is helium. Lithium is present in parts per billion, and even that small number matters for tests. There are essentially no heavier elements at this stage, and that absence is as informative as any presence. Carbon, oxygen, silicon, and iron are not missing by accident. They require stars, and stars have not formed yet. Heavier nuclei need repeated fusion steps, and in many cases, explosive conditions to be synthesized and dispersed. The early universe does not have long-lived gravitational furnaces, and it does not yet have the cycles of birth and death that enrich space. This is the first boundary between chemical possibility and chemical richness. The universe can eventually allow chemistry, but it cannot yet supply many ingredients. Early matter is like a language with only a few letters, capable of forming words, but not poetry. Complexity will come later, but only if gravity can gather this simple gas. For hundreds of thousands of years, the plasma remains ionized and opaque. Electrons keep photons trapped through Thomson scattering, and the radiation field keeps matter tightly coupled. Pressure from radiation resists gravitational collapse on many scales. Density variations exist, but baryonic matter cannot easily fall into them while tied to light. Those variations are real, yet they are constrained. Regions that are slightly denser also tend to be slightly hotter, and the photon pressure in those regions pushes outward. The plasma supports sound waves, literal acoustic oscillations on cosmic scales. These waves compress and rarefy the fluid, leaving a patterned imprint rather than random blotches. If you could see it, the universe would resemble a shimmering ocean of energy. Overdensities would be gentle swells, not sharp peaks, because radiation smooths extremes. The plasma rings with oscillations set by gravity, pulling inward, and pressure pushing outward. The universe is conducting a slow, enormous symphony, and the score will later be readable. The key transition is recombination, when electrons finally stick to nuclei. The name is historical and slightly misleading because it is the first true combination into neutral atoms. The process begins when the temperature drops to a few thousand Kelvin. At that point, typical photons lack the energy to ionize hydrogen efficiently. This does not mean ionizing photons vanish. It means their tail in the high energy distribution becomes rare enough that neutral atoms can survive. The balance tips because the universe expands, cools, and dilutes the radiation field. In equilibrium terms, the ionization fraction falls steeply once conditions cross a threshold. Recombination is not a single instant across the entire cosmos. It is a rapid shift in a changing environment, spread over a range of redshifts. The transition has a thickness in time because photons and atoms interact through many pathways. Some recombination routes produce photons that can reionize nearby atoms, delaying the net conversion. Helium recombines first because it binds electrons more tightly. Hydrogen follows, and because hydrogen is so abundant, it dominates the story. In the visuals, the plasma's glow does not switch off like a lamp. It fades in a physically meaningful way as the scattering fog thins and the photon paths lengthen. Neutral atoms matter for one decisive reason. Free electrons are the main scatterers of photons in this era. When electrons become bound inside atoms, the scattering rate collapses. The universe becomes transparent, and photons begin to travel long distances without constant interruption. Transparency here is a statistical statement. It means the mean free path of a typical photon becomes comparable to, and then vastly larger than, the scales we care about. Light stops being trapped locally and starts free streaming across the cosmos. The universe transitions from a diffusive regime where photons random walk to a ballistic regime where they travel almost straight. This is photon decoupling, when radiation stops behaving like part of the matter fluid. Light is no longer trapped in the plasma, and it streams outward through expanding space. The photons that escape become the cosmic microwave background. They are not emitted by a single object. They are released by a change in the universe's ability to hide them. The phrase, surface of last scattering, helps the mind. But it is not a solid wall. It is a fuzzy shell in space-time, defined by probability. Most photons last interacted with electrons within a narrow window, but not at an identical moment. Still, the effect is sharp enough that we can treat it as an image. The CMB is therefore an afterglow with a precise origin. It comes from the surface of last scattering, the moment most photons last interacted with free electrons. It carries a record of temperature and density variations imprinted in the plasma. Those variations are small, but they are the seeds that gravity will later amplify. The smallness is part of the mystery. The CMB's temperature varies by only tens of microkelvin across the sky, against a background near 2.7 Kelvin today. That is a contrast of about 1 part in 100,000. Yet from such slight unevenness, the universe eventually builds galaxies, clusters, and the intricate web of cosmic structure. This chapter stays focused on what recombination makes possible. It turns a charged, light-trapping medium into a mostly neutral gas. It changes how pressure works, how sound waves freeze, and how matter can begin to fall. It also creates the oldest image we can ever see with light. When sound waves freeze, they do not disappear. Their pattern becomes encoded in the distribution of matter and in the temperature anisotropies of the CMB. The peaks and troughs of those oscillations later echo in galaxy clustering, a fossil rhythm called baryon acoustic oscillations. The early universe leaves multiple copies of the same story, written in different media. The universe, after recombination, is often called the cosmic dark ages. That darkness is not emptiness, and it is not a lack of physics. It is a lack of luminous sources because stars have not ignited yet. The gas is present, mostly hydrogen and helium, and it is cooling further as expansion continues. Visually, this is a quiet epoch. There are no points of starlight, no glowing nebulae, and no galaxies. Instead, there is a vast, nearly uniform haze of neutral gas with subtle density ripples inherited from earlier times. The darkness is therefore a kind of waiting, matter poised between smoothness and collapse. Neutral gas behaves differently under gravity than plasma tied to radiation. Baryons can now drift more freely into gravitational potential wells. Many of those wells are dominated by dark matter, which began clumping earlier. Even without naming every model, the effect is clear. Gravity finally gets a cleaner chance to concentrate ordinary matter. Dark matter's role is crucial because it does not feel radiation pressure. It can begin to form over dense regions while baryons are still constrained by the photon bath. By the time recombination occurs, a scaffolding of potential wells already exists. Baryonic gas can then fall into that scaffolding, adding mass and enabling the next stage of structure. Yet cooling alone does not guarantee collapse. Gas must lose energy to contract because compression heats it and raises pressure. A cloud that cannot radiate away its heat will stall, supported by its own thermal motion. In a universe with only hydrogen and helium, cooling channels are limited, especially at low temperatures. Atomic hydrogen can cool gas through electronic transitions, but those transitions require relatively high temperatures to excite. Below certain thresholds, the gas becomes inefficient at shedding energy through atomic lines. This is where the first molecules become crucial, even in tiny amounts. A small chemical change can create a large dynamical consequence. The earliest chemistry is sparse, but it is not zero. A small residual fraction of free electrons remains after recombination, because recombination never goes to absolute completion. Those electrons act as catalysts for molecular formation. They enable pathways that would be inefficient in a perfectly neutral gas. In the visuals, think of these electrons as rare sparks in a cooling mist. They are not numerous, but they are chemically influential. Because reaction rates depend on collision partners, even a trace population can open a channel that otherwise would be closed. The early universe is full of such leverage points, small fractions that steer big outcomes. One key route forms molecular hydrogen, H2, through intermediate ions. An electron can attach to hydrogen, forming H-. That ion can react with another hydrogen atom to produce H2 and release the electron. The electron returns to the pool, ready to catalyze again, which is why this pathway can operate despite scarcity. Another route uses H2+, formed when a proton binds to hydrogen, then reacts again. Both routes compete with destruction mechanisms, including collisions and photodissociation. The balance depends on density, temperature, and the background radiation field. Chemistry here is not a laboratory flask. It is a moving target in an expanding universe. The details are technical, but the consequence is simple. Even a tiny fraction of H2 can radiate energy through rotational and vibrational transitions. That radiation lets gas cool below the limits set by atomic hydrogen alone. Cooling lowers pressure support, and it helps gravity compress gas clouds. Molecular cooling works because molecules have quantized energy levels that can be excited by collisions. When an excited molecule decays, it emits a photon that can escape, carrying energy away. In plain terms, molecules provide extra rungs on the ladder for the gas to step down in temperature. Without those rungs, the gas stays warmer and more resistant to collapse. Other simple species can form in trace amounts. Deuterium can participate to make HD, which can be an even more effective coolant at low temperatures. Because HD has a small electric dipole moment, it can radiate more efficiently than H2 in certain regimes. That efficiency matters most when the gas is already relatively cool and needs a final push downward. Helium hydride, He+, may appear briefly as one of the first molecular ions. It is a chemically simple molecule, yet it represents a conceptual milestone. It shows that once the universe cools enough, even the earliest ingredients can begin to assemble into bound structures. The first bonds are tentative, but they are real. These molecules are rare, but their cooling impact can be disproportionate. A cloud does not need to be mostly molecular to benefit from molecular cooling. It needs only enough molecules to radiate away the heat generated by gravitational compression. In that sense, early chemistry is less about abundance and more about influence. This is the bridge from chemical possibility to astrophysical consequence. Molecules do not make the universe chemically rich yet. They make it physically cooperative because they help gas shed heat. Without efficient cooling, the first stars would form later, or in different masses, or perhaps not at all. The simplicity of primordial chemistry also sets constraints on early star formation. With no metals and little dust, gas clouds fragment differently. Metals and dust in later epochs provide strong cooling and many pathways for small clumps to form. In the primordial case, fragmentation is limited, and the typical collapsing mass scale is expected to be larger. The first stars are therefore expected to be massive, short-lived, and intense in ultraviolet radiation. That expectation connects back to chemistry, because early radiation can destroy molecules and reionize gas. A massive star does not merely light up its surroundings. It changes the chemical rules for the next generation. So the first chemistry is fragile. H2 forms slowly and can be broken by photons in the Lyman-Werner bands. Even before the universe has many stars, background radiation can build up locally around the earliest sources. A feedback loop begins. where the first light both enables and suppresses later collapse. This feedback is one of the chapter's quiet tensions. Cooling helps collapse. Collapse makes stars, and stars emit radiation that can erase the very molecules that allowed collapse. The universe is learning to build structure while simultaneously learning to regulate it. That self-interaction is one reason the early stages are difficult to model cleanly. This chapter also clarifies what the early universe does not yet have. It does not have carbon-based chemistry because carbon does not exist in bulk. It does not have water because oxygen is absent. It does not have dust grains, which in later epochs provide surfaces that accelerate molecule formation. Dust is especially important later because it acts like a chemical workshop. On dust-grained surfaces, hydrogen atoms can meet and form H2 efficiently, then depart into the gas. In the primordial universe, that surface chemistry is missing, so the gas must rely on slower gas phase pathways. The universe is chemically possible in principle, but chemically poor in practice. That poverty is not a disappointment, but a clue. It tells us that complexity must be built, not assumed. Heavier elements require nuclear furnaces inside stars and explosive dispersal afterward. The interstellar medium's later diversity is a product of stellar life cycles, not primordial abundance. In this light, recombination is not just a technical milestone. It is the moment the universe becomes capable of keeping stable, neutral building blocks long enough for history to accumulate. Before recombination, matter is constantly reset by radiation. After recombination, matter can persist, cool, and respond to gravity with fewer constraints. Primordial element abundances remain one of cosmology's strongest tests. The predicted helium fraction depends on the expansion rate and the number of light particle species. Deuterium abundance is especially sensitive to baryon density because deuterium is easily destroyed in nuclear reactions. If the baryon density were higher, more deuterium would be burned into helium. These predictions are not vague. They arise from a network of nuclear reaction rates, the neutron-to-proton ratio set by weak interactions, and the timing of when reactions freeze out. The early universe functions like a controlled experiment because its initial conditions are simple and its evolution is governed by well-understood physics. When observations match predictions, it is a powerful confirmation. Lithium is the troublemaker, because observed lithium in old stars often disagrees with simple predictions. The mismatch is not enormous, but it is persistent. It sits in the uncomfortable zone between measurement uncertainty and theoretical confidence. That is exactly where scientific mysteries tend to live. The lithium problem is a reminder that early universe physics can be precise and still incomplete. The discrepancy could reflect stellar depletion, unmodeled nuclear reactions, or new physics. It could also reflect how hard it is to measure primordial lithium cleanly, because stars can alter their surface abundances over time. In a documentary about mysteries, it is a small crack that invites larger questions. Are we missing a subtle astrophysical process that hides lithium? Are nuclear rates slightly different under early conditions than we assume? Or is there a faint hint of new particles or interactions that changed the early chemistry? The chapter does not answer, but it frames the puzzle. Recombination itself also contains subtle uncertainties. The process depends on atomic transition rates, radiative transfer, and the exact thermal history. Modern calculations are sophisticated because CMB measurements are precise. Small modeling errors can bias inferred cosmological parameters, and those parameters shape our entire cosmic narrative. One reason recombination is tricky is that hydrogen cannot simply drop directly to its ground state and emit a single photon. Some photons would be immediately reabsorbed, and certain transitions are forbidden or suppressed by quantum rules. The atom must cascade through intermediate states, and the emitted radiation interacts with the surrounding medium. The transparency of the universe is a clean idea, but the details must be earned. Now we return to the deeper mystery introduced in Chapter 1. The CMB shows tiny temperature variations that correspond to density variations. Those variations are the seeds of later structure, but their origin is still debated in its deepest sense. Inflation is one leading explanation, but it is not the only conceptual framework. Whatever their origin, the variations must have the right amplitude and statistical pattern. Too small, and gravity would not build galaxies by today. Too large, and the universe would collapse into black holes early. The observed pattern sits in a narrow window that feels tuned, even if physics can explain it. It is worth lingering on what pattern means. The fluctuations are not just random speckles. They have correlations across angles on the sky, and those correlations encode the physics of the early plasma. Peaks in the CMB power spectrum reflect acoustic oscillations, while the overall tilt reflects how fluctuations vary with scale. The universe is leaving a fingerprint, not a blur. We also face the question of how those variations translate into the first collapsed objects. Dark matter can begin clumping earlier because it does not couple to photons. Baryons join later, after recombination, when pressure and scattering no longer dominate. The handoff from radiation control to matter control is one of the universe's most important regime changes. That handoff is also a change in what counts as resistance. Before recombination, photon pressure and tight coupling resist collapse. After recombination, thermal pressure in the gas becomes the main opposing force, and that pressure can be reduced by radiative cooling. Chemistry, therefore, becomes a tool of gravity, an unexpected partnership between microscopic transitions and cosmic architecture. Early chemistry proceeds inside that handoff. Molecules form in a background of cooling gas and expanding space. They form under weak but evolving radiation fields, including the CMB itself. They form in regions with slightly different densities, because density controls reaction rates. Small differences can compound over time. A slightly denser region has more collisions, so it forms molecules faster. More molecules allow more cooling, which permits more contraction, which increases density further. This is not yet runaway star formation, but it is the logic of amplification. The universe is full of feedback loops, and the earliest ones begin with almost imperceptible contrasts. This is where uncertainties remain. Active research rather than settled textbook. We do not fully know the detailed molecular abundances in the first mini-halos. We do not fully know how early radiation from the first stars propagates through clumpy gas. We do not fully know how magnetic fields, turbulence, and streaming velocities between baryons and dark matter affect collapse. Even the phrase density fluctuation hides complexity. Fluctuations have a spectrum across scales, and different scales enter causal contact at different times. Acoustic oscillations in the plasma leave imprints that later appear in both the CMB and galaxy clustering. The early universe is not just smooth plus noise. It is smooth plus patterned ripples governed by known physics. Those ripples freeze into the afterglow at decoupling. The CMB becomes a map of conditions. At the moment, the universe turns transparent. It is a snapshot of a plasma becoming gas and of sound waves becoming statistics. It is also a boundary. We can look back to it, but not through it with ordinary light. The boundary has a visual metaphor that fits the science. Before decoupling, the universe is like a dense fog where headlights only illuminate a few meters. After decoupling, the fog lifts and the same light can travel across continents. The lifting is not magic. It is the disappearance of free electrons as dominant scatterers. So, recombination is both an ending and a beginning. It ends the era when photons are trapped and matter is ionized. It begins the era when light can travel and matter can cool into neutral structures. It sets the stage for the first stars by allowing gravity and chemistry to cooperate. The central question tightens here. If galaxies and worlds grew from near uniform beginnings, then the first stable atoms are the first durable building blocks. They are not yet planets or life, but they are the first time matter can keep its shape. The universe becomes a place where history can accumulate. We can also place this moment in human history. The idea that atoms formed long after the beginning is modern, tied to plasma physics and quantum theory. Early cosmologists learned to treat the universe as a thermodynamic system, where temperature and density determine what states of matter can exist. That shift in thinking turned the cosmos into something calculable. The prediction of a relic radiation field came before its discovery. It was a logical consequence of a hot, dense beginning and an expanding universe. When the cosmic microwave background was detected in the 20th century, it did more than confirm a theory. It turned a theoretical timeline into an observed one, and it forced recombination into the center of cosmology. The discovery also changed how we imagine evidence. Instead of relying only on galaxies and stars, cosmology gained a direct signal from an era before any star ever shone. The CMB is not a fossil in rock. It is a fossil in light, arriving continuously from every direction. Today, precision cosmology treats recombination as a calibrated epoch. Satellites measure the CMB power spectrum, and models translate it into parameters like baryon density and expansion rate. That translation depends on understanding atomic physics in an expanding universe. The cosmic story depends on the smallest bound states. When we say smallest, we mean it literally. The binding energy of hydrogen, the fine structure of atomic levels, and the rates of photon emission and absorption all feed into the shape of the CMB anisotropies. A slight change in recombination history shifts the thickness of the last scattering surface. That shift subtly alters the observed spectrum, and the universe notices. Still, the mystery tone remains justified. We have a clear mechanism for transparency, but we do not have a complete explanation for the initial seeds. We have plausible molecular pathways, but we do not have direct observations of the first chemistry in action. We have predictions for the first stars, but we are still testing them with new telescopes. That gap between mechanism and origin is where wonder persists. We can compute when neutral hydrogen forms. Yet we still ask why the initial fluctuations had the form they did. We can model H2 formation, yet we still ask how early radiation and gas dynamics shaped the first collapses. The early universe is both a solved problem and an open one, depending on where you look. The chapter closes by leaning into the next observational anchor. Once neutral atoms form, photons decouple and begin their long journey. That journey preserves an image of the universe at about 380,000 years old. In the next chapter, we read that image as evidence, and we ask what it reveals about the first seeds of structure. The universe cools into reality, and reality leaves a record. The afterglow is faint, but it is everywhere. It is the oldest light we can see, and it is our most important clue. When we listen closely to that light, when we treat it as a message rather than a backdrop, we hear the universe describing its first stable forms. And behind that description sits a final, quiet question. If the earliest atoms are the first durable building blocks, what else was made durable at the same moment? Matter, information, or the very possibility of memory in the cosmos? The CMB does not answer directly, but it invites us to keep looking. Chapter 2 ended when the universe turned transparent and the oldest light escaped. Chapter 3 begins by treating that light as evidence, not atmosphere, because in cosmology, even a faint glow can behave like a document. The cosmic microwave background is a nearly uniform microwave sheen, arriving from every direction with uncanny steadiness. On screen, it looks like a soft, mottled sphere wrapped around us, an all-sky photograph of a time when the universe was young. It is the earliest electromagnetic signal we can observe directly, and it anchors our timeline with a timestamp written in temperature. The CMB comes from the surface of last scattering, about 380,000 years after the beginning, when the universe had cooled to roughly a few thousand Kelvin. Before that moment, the cosmos was an ionized plasma, where electrons and atomic nuclei moved freely, and photons could not travel far. Light was trapped in a dense fog of charged particles, ricocheting from electron to electron through Thomson scattering. If we could stand there, we would not see stars or darkness, only a blinding, uniform radiance with no clear direction. After recombination, most electrons bound into neutral hydrogen and helium, and the scattering rate collapsed. Photons began free streaming, and the universe became transparent in a physical, measurable sense. That release created a snapshot, because the last interactions happened within a narrow window rather than at a single instant. The surface of last scattering is really a thin shell with thickness set by atomic physics and the expansion rate. In visual terms, it is like a glowing fog bank that suddenly thins, revealing a final shimmer before the light escapes forever. As the universe expands, those photons stretch with it, their wavelengths lengthening from visible and infrared into microwaves. Today they arrive as a black body spectrum at about 2.7 Kelvin, a near-perfect thermal curve that is as informative as it is simple. The snapshot looks smooth at first glance, and the smoothness is the problem that drives the story forward. A perfectly uniform universe would not build galaxies, because gravity would have nothing to prefer and nowhere to begin. The CMB is uniform to about 1 part in 100,000. Yet structure exists today on scales from galaxies to vast clusters. The crucial information is in the tiny anisotropies, the mottled pattern of slightly hotter and colder spots. They are small enough to miss in a casual glance, yet coherent enough to map with precision. Those spots are not weather, and they are not random noise, even though the map resembles a speckled atmosphere. They are temperature differences of tens of microkelvin, measured across the full sky with instruments cooled near absolute zero. Each pixel on a modern map represents a statistical estimate built from repeated scans, careful calibration, and years of data. The pattern encodes small differences in density and motion in the primordial plasma, and it also encodes gravitational potentials that were already present. Those potentials were dominated by dark matter, which shaped the landscape without shining. A slightly hotter patch often traces a region that was slightly denser, but the link is subtle and sometimes counterintuitive. Denser regions compress the plasma and can raise temperature through pressure and gravitational heating, leaving a warm imprint. Yet photons climbing out of deeper gravitational wells lose energy, which can make dense regions appear colder when they finally escape. Motion matters too, because plasma moving toward us Doppler shifts the radiation slightly hotter, while motion away shifts it slightly cooler. The CMB therefore records competing effects: compression, gravitational redshift, and velocity, so the pattern becomes a physics ledger rather than a simple density map. The key idea is simple enough to hold without equations, even if the underlying machinery is intricate. Where density was slightly higher, gravity pulled a little harder, and matter tended to drift inward over time. Where density was slightly lower, gravity pulled a little less, and matter tended to thin out as surrounding regions stole material. These differences were tiny, but gravity amplifies tiny differences over long times, especially when the universe has billions of years to work. In that sense, the CMB is not a picture of galaxies. It is a picture of the conditions that made galaxies possible. Gravity is not creative, but it is relentlessly selective, and it rewards any place where mass gathers by making that place even more attractive. It turns small initial contrasts into larger contrasts, because attraction strengthens where mass accumulates and weakens where mass is scarce. The early universe also expanded rapidly, which fought against collapse on large scales by stretching space itself. Structure formation is therefore a race between inward pull and outward stretching, and the outcome depends on the balance at each scale. Some ripples grow, some stall, and some are erased by pressure and diffusion. In the plasma era, pressure mattered as much as gravity, and the universe behaved like a coupled fluid with a very unusual ingredient. Photons and baryons moved together because electrons tied the radiation to the matter through constant scattering. Radiation pressure resisted compression, acting like a spring that pushed back when gravity tried to squeeze. When gravity pulled matter inward, pressure pushed outward, and the fluid oscillated. These oscillations were sound waves on cosmic scales, driven by gravity and restored by radiation pressure, propagating at a significant fraction of light speed. Acoustic oscillations are the CMB's hidden soundtrack, preserved as a statistical pattern rather than an audible tone. They do not appear as obvious rings in the map because we see a projection of many waves at many distances. Instead, they show up as peaks in the angular power spectrum, a plot that summarizes how much variation exists at each angular scale. Each peak corresponds to a preferred scale, set by how far sound could travel before decoupling. That distance is the sound horizon, and it becomes a standard ruler that cosmologists carry forward through time. The first peak tells us about geometry, because angles depend on curvature, and the universe acts like a lens. If space is flat, the sound horizon appears at a specific angular size, roughly a degree on the sky. If space were strongly curved, the same physical scale would look larger or smaller, shifted left or right in the spectrum. The observed peak positions indicate a universe very close to flat, within tight uncertainties that have narrowed with each generation of data. That result is not just abstract geometry. It sets the stage for how volumes, distances, and growth unfold. The relative heights of the peaks tell us what the universe was made of, and they do it in a way that feels almost like spectroscopy for cosmic composition. Baryons add inertia to the photon-baryon fluid, enhancing compressions relative to rarefactions, so certain peaks rise while others fall. Dark matter deepens gravitational wells without adding photon pressure, changing how oscillations grow and how quickly they fall back. The pattern lets us infer baryon density and total matter density separately, which is why the CMB can tell us that most matter is not made of atoms. In the power spectrum, composition becomes a fingerprint. The damping tail, where small-scale fluctuations fade, adds timing information that is easy to overlook. Photon diffusion, often called silk damping, lets photons random walk out of small overdensities, smoothing the tiniest features before the final release. The finite thickness of last scattering adds another blur, because the snapshot is not infinitely thin. That blurring depends on the expansion rate and the ionization history, which are themselves tied to particle content and early universe dynamics. The CMB, therefore, constrains not only ingredients, but also the pace of early expansion and the microphysics of recombination. This is where the CMB becomes a parameter machine, and the phrase is not an exaggeration. From one sky map, we infer the baryon fraction, the dark matter fraction, and the overall energy budget that includes dark energy. We infer the Hubble constant in a model-dependent way, because the conversion from angles to distances assumes a specific cosmic framework. We infer the age of the universe, not by counting stars, but by fitting an expansion history that matches the acoustic pattern. We also infer the initial fluctuation spectrum, including its amplitude and its slight tilt with scale. The tilt matters because it hints at the origin of the ripples, and it gives the early universe a distinctive texture. The observed spectrum is close to scale invariant, meaning similar power across many scales, with a small deviation that carries theoretical weight. That is consistent with inflationary ideas, where quantum fluctuations are stretched to cosmic sizes as space expands extremely rapidly. In that picture, randomness at microscopic scales becomes structure at astronomical scales, and the CMB preserves the statistical signature. It is not a direct proof of inflation, but it is a strong compatibility check that keeps inflation in the conversation. The CMB also tests whether the early fluctuations were mostly adiabatic and nearly Gaussian, which are technical words with simple implications. Adiabatic means matter and radiation varied together, so the universe was perturbed without changing the overall entropy pattern between components. Gaussian means the statistics resemble random fields with simple correlations, where the map is largely described by its two-point function. The data largely support these properties, and that support narrows the space of viable early universe models. It also suggests that the seeds were simple, even if their origin was not. Yet the origin question remains open at the deepest level, and the CMB's precision makes that openness feel sharper. Even if inflation explains the mechanism, it does not settle the cause, and mechanism is not the same as reason. What field drove inflation, and why did it start in the first place, rather than never beginning or never ending? Why did it end when it did, leaving the specific amplitude we observe rather than a universe too smooth or too violent? The CMB constrains scenarios, but it does not reveal the trigger, only the aftermath. The CMB also marks a hard observational boundary, and the boundary is written into the interaction between light and matter. We cannot see earlier with light because the universe was opaque before decoupling, and opacity is a physical wall. That boundary is not a limitation of telescopes, but of scattering physics and the density of free electrons. Beyond it, we rely on indirect messengers, like primordial element abundances and later structure, which carry integrated clues rather than direct images. The CMB is therefore both a window and a curtain. Some messengers might eventually look behind the curtain, but they are difficult, and difficulty is part of the drama. Primordial gravitational waves could carry information from earlier times because they interact weakly and travel almost unimpeded. Their signature might appear as B-mode polarization in the CMB, a subtle, swirling pattern distinct from the gradient-like E-modes. Foregrounds and systematics complicate the search because dust in our own galaxy can mimic the signal. If detected cleanly, such waves would open a new window on the earliest moments and force us to rewrite parts of the origin story. Polarization already adds a second layer to the map we can read, turning temperature into a richer language. E-mode polarization traces velocity patterns in the plasma at last scattering, because moving electrons scatter light in a way that imprints a preferred orientation. In visuals, polarization overlays look like tiny strokes of paint aligned across the sky, revealing flows we cannot otherwise see. It sharpens constraints on parameters and helps separate effects like reionization, when later stars reionized hydrogen and rescattered some CMB photons. It also provides consistency checks that protect us from fooling ourselves when noise and bias tempt interpretation. Reading the CMB requires a careful relationship between observation and theory, and the relationship is a disciplined loop rather than a one-way translation. Observational astronomy measures microwave intensity across frequencies, scanning the sky repeatedly to build redundancy and reduce drift. Instruments must be calibrated, cooled, and shielded from stray emission, because even a warm component on the spacecraft can glow in microwaves. The detectors, bolometers, radiometers, and polarization-sensitive arrays must distinguish microkelvin variations against a 2.7 Kelvin background. The signal is faint and the contaminants are bright, so the craft is as much engineering as it is astronomy. Foregrounds are the first obstacle, because the Milky Way is in the way, and it refuses to be quiet. Galactic dust emits microwaves with a spectrum that rises at higher frequencies, painting the sky with filamentary haze. Synchrotron radiation from electrons spiraling in magnetic fields rises at low frequencies, especially along the galactic plane. Free emission adds another component, produced when electrons scatter off ions without binding. Extragalactic sources add point-like contamination, and clusters distort the spectrum through the Sunyaev-Zeldovich effect, where hot electrons boost photon energies. The CMB is recovered by multi-frequency mapping and statistical separation, not by a single clean photograph. Space missions changed what was possible because they escape atmospheric noise that otherwise swamps delicate measurements. COBE first measured the CMB's black body spectrum precisely, showing it was astonishingly close to a perfect thermal curve and confirming the hot Big Bang picture. COBE also detected anisotropies at large scales, a discovery that turned theory into a measurable program. WMAP mapped the sky with higher resolution and established the standard cosmological parameter set with clarity that made textbooks catch up. Planck pushed precision further, tightening constraints and exposing small tensions that now motivate new observations. Ground-based and balloon experiments complement satellites by targeting smaller angular scales, where the damping, tail, and lensing signatures live. They trade full sky coverage for higher resolution and sensitivity in selected patches, often chosen for low foreground emission. In visuals, these observatories sit on high deserts and polar plateaus, where dry air reduces microwave absorption. They also test new detector technologies and polarization strategies, building the next generation of instruments. Together, these instruments build a layered picture, independent methods cross-checking the same physics from different angles. Theoretical astrophysics turns maps into numbers by comparing data to predicted spectra, and the comparison is both rigorous and delicate. A cosmological model specifies ingredients, initial conditions, and expansion history, including how radiation, matter, and dark energy evolve. Boltzmann codes compute how perturbations evolve through radiation and matter eras, tracking coupled fluids, gravitational potentials, and photon transport. The output is a predicted temperature and polarization spectrum, which can be compared directly to the measured one. Statistical inference then finds the parameter values that best match the observed sky, with uncertainties that reflect both noise and cosmic variance. This translation is powerful, but it is not automatic truth, and precision makes that clear rather than comforting. It depends on assumptions, like the form of dark energy and the number of light particle species that behave like neutrinos. It depends on recombination physics, including subtle atomic transitions and the exact timing of electron capture. It depends on calibration choices and beam modeling, because a slightly mismeasured instrument response can shift inferred parameters. Precision makes these dependencies visible, because small modeling errors can bias big conclusions when the error bars are tight. Some of those conclusions are now central to the structure story, and they reshape our intuitive picture of what the universe contains. The CMB indicates that ordinary baryonic matter is only a small fraction of the total, even though it is the part that makes stars and people. It indicates that most matter is dark, interacting primarily through gravity and leaving its mark through potential wells. It indicates that most of the energy budget is something like dark energy, affecting expansion at late times and slowing the growth of structure. These are not philosophical claims. They are inferences from patterns in a microwave sky. These inferences connect directly to how galaxies form on schedule, rather than remaining abstract numbers on a plot. Dark matter can begin clumping earlier because it does not couple to photons and does not feel radiation pressure. It forms potential wells that deepen while baryons are still pressured by radiation, creating a scaffolding that is invisible yet decisive. After recombination, baryons fall into those wells, and the growth of structure accelerates as gas collects and cools. The CMB anisotropies are therefore the blueprint for the cosmic web, but only in outline. The initial ripples are small and nearly linear, meaning they can be described as small perturbations superimposed on an otherwise uniform background. Over time, gravity makes them non-linear, turning gentle hills into sharp peaks and empty basins, and the mathematics becomes more complex. The late universe is the same pattern, evolved into filaments, nodes, and voids, with galaxies forming where the density becomes high enough for gas to cool efficiently. In visuals, simulations show a faint mist condensing into strands, then thickening into knots that glow with star formation. The web is the grown-up version of a micro-Kelvin map. The cosmic web is not an artistic metaphor, but a dynamical outcome that emerges from simple rules applied over immense time. Regions slightly denser than average attract more matter and become filaments and clusters, where gravity funnels material along preferred paths. Regions slightly underdense lose matter to their surroundings and become voids, expanding faster than average because there is less mass to slow them. The web's geometry reflects the initial fluctuation spectrum filtered through gravity and expansion, like a melody transformed by the acoustics of a vast hall. When we map galaxies today, we are seeing the late-time echo of early ripples. Simulations show this growth with unsettling clarity because they let us watch billions of years in minutes. Start with a CMB consistent field of tiny perturbations and add gravity, dark matter, and expanding space, and the pattern almost inevitably forms. Halos form first on small scales, then merge into larger structures, building a hierarchy of mass. Gas falls in, shocks, cools, and eventually forms stars, but only after the dark scaffolding is built and deep enough to hold it. The CMB does not show us those halos directly, yet it predicts their statistical distribution. The CMB also leaves a later echo in galaxy clustering through baryon acoustic oscillations, a fossil of the same sound waves. In the early universe, the photon-baryon fluid pushed outward from overdensities, leaving a slight preference for matter to be separated by the sound horizon scale. After decoupling, that preference freezes into the distribution of galaxies as a subtle bump in the correlation function. Measuring that scale at different redshifts traces the expansion history because the ruler appears at different angular and distance scales over time. It provides an independent ruler that links the early universe to the late universe, tying microwave maps to galaxy surveys. This link is one reason the CMB is more than a relic, because it calibrates the entire cosmic timeline. It ties early physics to late structure, turning cosmology into a connected narrative rather than a set of disconnected measurements. It also reveals where the narrative strains, because some measurements do not align perfectly across methods. The CMB is stable enough to serve as a reference, yet precise enough to expose mismatch. In that tension, mystery returns, not as ignorance, but as a clue. One tension is the Hubble constant discrepancy, which has become a recurring theme in modern cosmology. The CMB infers a value within the standard model because the acoustic pattern fixes distances when combined with an assumed expansion history. Local distance measurements often find a higher value, using calibrations based on standard candles and geometric methods. The difference could be systematic error, or it could hint at new physics beyond the simplest model, such as changes in early energy content. The CMB does not resolve the tension, but it defines one side of it sharply enough to be uncomfortable. Another tension involves the amount of clustering today compared with CMB predictions, often discussed through parameters that summarize structure amplitude. Weak lensing and galaxy surveys sometimes suggest slightly lower clustering than the CMB would predict under the simplest assumptions. The discrepancy is modest, but persistent across datasets, which keeps it from fading away as a statistical fluke. If it holds, it could imply changes in dark energy behavior, neutrino mass effects, or unrecognized observational biases in how we measure galaxies and shapes. The CMB again acts as a benchmark, forcing every alternative explanation to meet a high standard. These tensions matter because they touch the central question, which is how we get from near uniformity to the architecture of the cosmos. If our model of ingredients or early conditions is incomplete, then our story of how structure forms may be missing a chapter. The CMB is precise enough to expose these cracks, and it is also consistent enough to keep the cracks from becoming chaos. That combination is rare in science, and it is why the Afterglow remains a central character. It is both a confirmation and a challenge. The chapter's core mystery is not that the CMB exists, but that it is so informative despite looking so bland. A faint microwave glow carries a record of density, motion, composition, and geometry, and it does so across the entire sky. It works because the early universe was simple enough to model and uniform enough to treat statistically, which makes small deviations meaningful. The same simplicity that feels like nothing becomes a readable archive because the physics of plasma, gravity, and expansion is well understood in this regime. When we decode the map, we are exploiting that simplicity rather than being bored by it. Still, we should name what the CMB cannot tell us directly, because boundaries define the shape of knowledge. It cannot show us what happened before the universe became transparent, because light itself could not carry a clear message then. It cannot reveal the exact microphysics of inflation, if inflation occurred, because many different mechanisms can produce similar statistical outcomes. It cannot identify the particle nature of dark matter, even though it implies dark matter's abundance and gravitational role. The map tells us what is required, not what the dark component is. It also cannot explain why the initial conditions were set in a narrow, life-permitting range, a fact that lingers behind the numbers. Fluctuations had to be small enough to avoid early collapse into black holes, yet large enough to build galaxies by now. The universe had to expand and cool in a way that allowed atoms, then stars, then heavy elements, and then stable environments. The CMB shows that this happened, and it measures the amplitude that made it possible. It does not tell us why that amplitude was chosen by nature, or whether it could have been otherwise. We can frame the unknowns as three nested horizons, each one deeper than the last. The first is observational, the last scattering surface that blocks earlier light and sets a literal edge to electromagnetic sight. The second is theoretical, the limit of our models, when energies approach regimes we have not tested in accelerators or laboratories. The third is causal, the question of whether the earliest conditions are uniquely determined or contingent, perhaps dependent on deeper laws. The CMB sits at the boundary of the first horizon, while pointing toward the others. Even within what we can observe, interpretation requires care, because the map is a projection of a three-dimensional universe onto a two-dimensional sky. Hotter and colder spots are not simply clumps and voids because gravitational redshift and Doppler motion contribute, and those contributions can oppose each other. The map also mixes scales along the line of sight because different distances contribute to the same angular pattern. Extracting the underlying field requires models of projection and evolution, and those models must be tested against polarization and lensing signals. The triumph is that the pieces fit together across independent observables. Yet the overall message is robust across methods, and it remains one of the cleanest narratives in cosmology. The early universe contained tiny, coherent ripples in density and velocity, seeded by processes we can constrain but not fully explain. Those ripples were imprinted as temperature and polarization anisotropies in the CMB, preserving a statistical portrait of the primordial state. Gravity then amplified the ripples into the large-scale structure we observe today, with dark matter guiding the growth and baryons painting it with light. The afterglow is the bridge between a smooth beginning and a structured present. This is the bridge from near nothingness to architecture, and the bridge is built from micro-Kelvin differences. The CMB shows a universe that is almost featureless, but not perfectly so, and that not perfectly carries everything. The imperfections are small enough to look accidental, yet structured enough to be physical, and they repeat across the sky with measurable regularity. They are the seeds that later become filaments, galaxies, and the environments where planets can form. When the camera lingers on the map, it is lingering on the origin of all later complexity. The chapter returns to the documentary's central question with a sharper statement, and the statement is both satisfying and incomplete. Galaxies form because gravity amplifies primordial differences, and the CMB measures those differences directly with extraordinary fidelity. Our models explain much of the growth from seed to web, given dark matter and known physics, and they predict patterns we later confirm in surveys. The remaining mystery is why the seeds had their specific pattern, and what physics set the first conditions behind the observable curtain. The afterglow answers many questions while keeping the deepest one alive. We end by stepping forward in time, beyond the afterglow, into an era that is visually empty but dynamically busy. After decoupling, the universe becomes dark to our eyes because stars have not ignited yet and there are no bright beacons. The CMB continues traveling, cooling as space expands, its wavelengths stretching while it quietly fills the cosmos. Meanwhile, matter begins to gather in the dark, guided by gravitational wells that deepen and merge. In that darkness, the first structures start to form, and the next chapter follows their first light. After the afterglow fades into microwaves, the universe enters a long, literal night, and the last scattered glow slips beyond human eyes. Photons still cross space freely, but there are no stars yet to mint new, visible light. In a sky with no suns and no galaxies, darkness is not poetic. It is physical, measurable, and nearly complete. The Dark Ages begin after recombination and decoupling, when the cosmic microwave background is released and matter stops riding on radiation. Electrons and protons combine into neutral hydrogen, while helium forms alongside them, leaving only a thin residue of free charges. That leftover ionization is tiny, yet it matters, because it keeps chemistry barely alive in an otherwise simple gas. The medium is not empty space. but a dilute, cooling fog spread across an expanding volume, with density falling as the universe grows. In visible light, it is effectively invisible because there are no luminous sources and because neutral gas does not glow on its own. We reconstruct this era indirectly, like archaeologists inferring a vanished city from foundations and ash. We infer the Dark Ages through what comes before and what comes after, and that bracket is unusually tight. The CMB gives initial conditions, encoding temperature fluctuations and polarization patterns that map primordial density variations. Later, galaxies reveal the outcome of growth, showing where matter eventually gathered and how it organized into the cosmic web. Between them lies a span where gravity works quietly and chemistry stays simple. And the central question tightens because structure must begin without luminous signposts. Neutral hydrogen dominates the baryonic mass and sets the observational stakes because it fills nearly every region between the first halos. Hydrogen's 21-centimeter transition offers a potential tracer produced by a hyperfine flip in the atom's ground state. It is a forbidden, slow transition, so the signal is intrinsically faint even when hydrogen is abundant. Redshift then pushes that line into low radio frequencies, where Earth's ionosphere, human transmitters, and bright galactic foregrounds overwhelm it. So the Dark Ages are mapped more by theory and inference than by direct imaging, and that limitation shapes the tone of the science. We simulate the growth of structure, we calculate reaction networks, and we search for statistical imprints rather than photographs. The question becomes almost philosophical. How do you describe an epoch that refuses to shine, except through subtle fingerprints left on later light? The universe is cooling as it expands, and cooling changes what gravity can accomplish in practical terms. In the plasma era, radiation pressure fought compression, and baryons were dragged by photons through frequent scattering. Now baryons decouple from radiation and can respond more directly to gravitational potentials, sliding into wells rather than being held up by light. Those potentials are already seeded by dark matter, which began clumping earlier because it does not interact electromagnetically. In visual terms, imagine a faint, three-dimensional relief map etched into space. Dark matter provides the contours long before gas can settle into them. The density field is not uniform, but mottled with slight overdensities and underdensities. Initially, only parts per 100,000. Gravity amplifies those differences over time, and the amplification is slow enough to feel inevitable, yet fast enough to change everything. Growth is hierarchical because the initial fluctuation spectrum contains power on many scales, from small ripples to broad undulations. Small overdensities collapse first, forming the earliest bound halos, while larger structures take longer to gather themselves. Those halos merge and accrete, building larger structures over time, and the cosmic web begins as a statistical pattern and becomes a physical network. Filaments thicken, nodes deepen, and voids become emptier, as if the universe is learning how to draw. Gravity is the engine, but it is not the whole machine, because collapse is not just falling inward. For gas to collapse into dense cores, it must lose energy and shed pressure support, and that requires radiative cooling. Compression heats gas, and hot gas pushes back against further collapse, so the system can stall in a warm, puffy state. Cooling is therefore the gatekeeper that decides whether a halo becomes a star-forming site or a quiet reservoir. In the Dark Ages, the interstellar medium is not yet an interstellar medium in the modern sense, because there are no stars between which it can exist. There are no stellar winds, no supernova shocks, and no metal enrichment, and there is no dust to catalyze chemistry efficiently. The medium is primordial, mostly hydrogen and helium, with chemistry limited to a few pathways and a few fragile molecules. Its temperature and ionization state are set by expansion, by weak background radiation, and by the faint afterglow of the CMB itself. The earliest bound objects are often called mini-halos, and their masses are modest by later standards, closer to star cluster scales than galaxy scales. They form where dark matter density peaks become non-linear and detach from the Hubble flow, meaning local gravity overcomes cosmic expansion. Gas falls into these wells, shocks, and heats to the halo's virial temperature, converting gravitational energy into thermal motion. Whether it then cools enough to fragment depends on molecular physics, and on whether the halo is deep enough to hold onto its heated gas. A useful way to picture virialization is to imagine infalling material overshooting the center, colliding, and settling into a turbulent equilibrium. Gravity pulling inward while pressure pushes outward. The resulting temperature is not arbitrary. It scales with the halo's mass and size, and it sets the initial conditions for chemistry. In a universe with metals, many atoms and ions radiate efficiently and bleed heat away. But here the periodic table is still almost empty. That absence forces the first star formation problem into a narrow channel. Atomic hydrogen cooling is effective only above certain temperatures because its line transitions require excitation energies that low-temperature gas cannot easily reach. The Lyman alpha transition, for example, is powerful but demands relatively hot gas to populate excited states. With no metals to provide abundant line cooling, the gas can stall at relatively warm temperatures, hovering far above what later molecular clouds achieve. The first collapse, therefore, depends on molecules that can radiate at lower energies, even if they exist only in trace amounts. Molecular hydrogen is the crucial early coolant, even when its abundance is tiny compared with neutral hydrogen. It forms through gas phase reactions, enabled by residual electrons left from recombination, which act like chemical matchsticks in a cold room. One pathway uses H- as an intermediate. An electron attaches to hydrogen, then a second hydrogen atom joins, and the electron is released. Another pathway uses H2+ with similar dependence on local conditions, and both routes depend sensitively on temperature and density. These reactions are slow, and they compete with destruction mechanisms that can erase progress as quickly as it forms. Collisions can dissociate molecules in hot gas, while photons can break them apart once sources appear, especially in the Lyman-Werner bands. The balance depends on density, temperature, and the evolving radiation background, and it changes from halo to halo. In the Dark Ages, chemistry is sparse but dynamically decisive because cooling hinges on a molecule that is difficult to make and easy to destroy. H2 cooling radiates through rotational and vibrational transitions, which are excited when molecules collide in sufficiently dense gas. Emitted photons carry energy away if they escape, and escape depends on optical depth and geometry, not just chemistry. As the gas cools, pressure drops, and gravity gains leverage, allowing further contraction toward a central core. A small molecular fraction can therefore change the fate of an entire halo, turning a warm, stable cloud into a collapsing nursery. Deuterium adds a secondary channel that may matter in special cases, and it highlights how small ingredients can have outsized effects. HD can cool more efficiently at low temperatures than H2 because it has a permanent dipole moment and radiates more readily. If conditions allow enough HD formation, gas can cool closer to the CMB temperature floor, which is itself warmer at high redshift. That can alter fragmentation and shift the characteristic mass scale of collapsing clumps, potentially changing what kinds of stars are born. The CMB sets a moving temperature baseline, and that baseline is easy to forget because we live in a colder universe. At redshifts of 20 or 30, the background radiation is tens of Kelvin rather than 3, bathing every cloud in a faint thermal glow. Gas cannot cool below the CMB temperature if it remains coupled radiatively, because the background photons reheat it as fast as it radiates away energy. This means the earliest star-forming regions may have a higher minimum temperature than later ones, raising the gene's mass and biasing collapse toward larger fragments. Another subtle ingredient enters here, and it is easy to underestimate because it sounds like a technical footnote. Baryons and dark matter may have had a relative streaming velocity after recombination, a leftover from acoustic waves in the early plasma. That coherent motion can reduce gas accretion into small halos, smear out density peaks, and delay the first collapse in some regions. It is a reminder that gravity pulls is true, but initial conditions include velocity as well as density, and the universe remembers both. As halos grow, angular momentum becomes unavoidable because infall is never perfectly radial in a lumpy universe. Small torques from neighboring structures accumulate into rotation, and rotation can support a disk that slows direct collapse. The gas may spiral inward rather than plunge, and that spiral must shed angular momentum if it is to reach stellar densities. To form a star, the system must transport angular momentum outward, while mass moves inward, and that transport can be driven by turbulence, gravitational instabilities, or magnetic stresses. This is where magnetic fields become a possible actor, even if their origin is uncertain and their early strength is hard to measure. The early universe may have had tiny primordial seed fields, perhaps generated during phase transitions or inflation, or fields generated later by plasma processes and shocks. Turbulence and collapse can amplify weak fields through dynamo action, stretching and folding field lines as the gas churns. Even modest fields can influence how disks evolve and how they fragment, because magnetism couples to charged particles and can transmit stresses across otherwise neutral gas. Magnetic stresses can move angular momentum through magnetorotational instabilities in rotating gas, turning differential rotation into turbulence that acts like an effective viscosity. They can also couple gas to outflows, enabling jets that remove angular momentum and energy, and jets are an efficient escape valve in later star formation. In modern star-forming regions, these processes are central, but in the primordial case, they remain debated because ionization is low and the field geometry is unknown. The uncertainty is not whether magnetism exists, but how strong and organized it becomes early, and whether it has time to matter before collapse runs away. Magnetic fields also interact with ionization fraction, which is low in neutral gas, and coupling depends on how well-charged particles drag the neutrals. Ambipolar diffusion can let neutrals slip past field lines, weakening magnetic braking and changing how quickly disks can shed angular momentum. Ohmic dissipation and the Hall effect may also enter at high densities, altering the magnetic topology as the core contracts. The effectiveness of magnetism, therefore, depends on microphysical details that are hard to measure directly, and that uncertainty echoes through every prediction of the first stellar masses. Despite these uncertainties, the narrative logic is clear, and it is remarkably consistent across models. Gravity gathers matter into halos, cooling lets gas contract, and angular momentum must be redistributed before a compact object can form. The first stars appear when a collapsing core becomes dense and hot enough for nuclear fusion, igniting hydrogen into helium and releasing sustained energy. That ignition is a phase change in cosmic history because it introduces durable light sources where there had been only fading afterglow. The first stars are often grouped under the label Population 3, a term that carries historical weight from mid-20th century stellar population studies. The naming is backward. Population 1 are young, metal-rich stars like the Sun, while Population 2 are older and metal-poor. So Population 3 became the hypothetical, pristine first generation. The term is conceptual, marking stars formed from primordial composition with no metals, and it frames a simple question. What does star formation look like when the universe has only hydrogen and helium to work with? Without metal line cooling and dust, fragmentation is less efficient because the gas cannot radiate away heat as readily during collapse. Dust grains in later epochs act as tiny radiators and chemical factories, but here they do not exist, and the gas remains comparatively warm. The typical stellar mass is therefore expected to be higher than in later populations, not by a small factor, but potentially by orders of magnitude. Yet the expectation is probabilistic, not absolute, and the early universe rarely rewards certainty. Massive stars are expected for several linked reasons that reinforce each other across scales. Warmer gas has a higher Jeans mass, so larger clumps become gravitationally unstable before smaller ones can separate. Limited cooling reduces the tendency to break into many small cores, and high accretion rates can feed protostars rapidly in dense primordial environments. Radiation pressure and ionization feedback also behave differently when the surrounding gas is metal-free, changing how easily a protostar can keep growing. Yet this expectation is not a settled number, and it remains one of the chapter's key unknowns because it determines the universe's first chemical output. Some simulations produce extremely massive stars, perhaps tens to hundreds of solar masses, while others find fragmentation into multiple systems within a disk. Disk fragmentation, radiative feedback, and magnetic effects can all change the outcome, and small differences in initial turbulence can cascade into different stellar families. The first stellar initial mass function remains uncertain, and it controls everything that follows, from supernova types to black hole seeds. Once a protostar forms, feedback begins almost immediately, because light and heat appear before the star is fully grown. Radiation heats surrounding gas and can halt accretion by raising pressure, especially along polar directions where density is lower. Ultraviolet photons can ionize hydrogen, creating an H2 region that expands outward, and that expansion is a moving boundary between neutral and ionized phases. That ionized bubble changes chemistry by destroying molecules and raising temperature, and it can carve channels through which more radiation escapes. The first stars also emit Lyman, Werner photons that dissociate H2, cutting the very coolant that enabled collapse in the first place. This can suppress cooling in nearby halos and delay additional star formation, especially in the smallest potential wells. Feedback, therefore, has a dual character because it both marks success and imposes limits, and the balance may vary from region to region. The first light is not gentle. It is sharp, ultraviolet, and transformative, and it reshapes the environment that produced it. Because population 3 stars are expected to be massive, they are expected to be short-lived, burning through nuclear fuel with extravagant speed. Massive stars burn hotter and faster, and their lifetimes can be only a few million years, a blink even on early cosmic timescales. Some may collapse directly into black holes, swallowing their cores with little outward display, while others explode as supernovae that outshine entire young galaxies. Either outcome injects energy and, in some cases, the first heavy elements into surrounding gas, turning pristine clouds into chemically altered terrain. This is the first chemical turning point since primordial nucleosynthesis, and it is one of the most consequential transitions in the story. Heavy elements, metals in astronomical language, are forged in stellar cores and distributed by explosions and winds, and their presence changes the cooling curve dramatically. Metals provide new cooling channels through many atomic and ionic lines, allowing gas to radiate efficiently at temperatures where hydrogen and helium are nearly silent. They also enable dust formation, which later accelerates molecule production and changes fragmentation by providing surfaces for reactions and additional radiative pathways. The interstellar medium is transformed by this enrichment, even when enrichment is patchy and localized around the first explosions. A small metal fraction can lower cooling temperatures and allow smaller clumps to collapse, shifting star formation toward lower masses and longer-lived stars. That shift is not only chemical, but demographic, because long-lived, low-mass stars can survive to the present day as fossils. The transition from population 3 to population 2 is therefore a shift in both chemistry and survivability, and it determines whether any direct witnesses remain. Early black holes may also appear in this era, seeded by massive stellar remnants, and their role is both enticing and uncertain. If they accrete gas, they can shine as early quasars and add ionizing radiation to the surrounding medium, potentially accelerating reionization in their neighborhoods. They can also drive mechanical feedback through jets and winds, stirring gas and heating it, which can either suppress or reorganize star formation. Their abundance and growth rate remain major uncertainties in early structure formation, and the uncertainty matters because black holes can act as compact engines in a diffuse universe. As more sources turn on, the universe begins to change phase again, and the change is visible in the physics even when it is not yet visible to us. Neutral hydrogen becomes ionized. Once enough ultraviolet photons escape into the intergalactic medium, breaking atoms into protons and electrons. This is reionization, a gradual, patchy process rather than a single moment, and its patchiness is the clue that it is driven by discrete sources. It is the end of the Dark Ages in the strict sense, because it fills the cosmos with new light and new ionization, and it changes how gas responds to gravity. Reionization is often described in narrative terms as dawn spreading through fog, and the metaphor is accurate in a technical way. Ionized bubbles expand around early stars and galaxies, then overlap and merge, and their boundaries are shaped by density contrasts in the surrounding medium. The topology depends on where the first sources form, how clustered they are, and how easily photons escape from their host halos. The process is uneven, leaving neutral islands that persist longer in some regions, like pockets of night that refuse to lift. Ionization changes how matter clumps and how we observe the distant universe. Because ionized gas is hotter and hotter, gas resists collapse. Higher temperature raises the Jeans scale, meaning small halos that could once gather gas may now fail to hold it against pressure. That can suppress gas accretion into small halos and reduce star formation in the smallest systems, effectively rewriting the minimum galaxy mass. Ionization therefore acts as feedback on structure growth, not just a lighting event, and it couples the fate of tiny halos to the radiation of their brighter neighbors. It also changes observational signatures in ways that allow us to triangulate the timeline. Neutral hydrogen absorbs specific wavelengths, producing the gun. Peterson trough in quasar spectra at high redshift, a sudden darkness where transmission should be. The CMB polarization records an integrated imprint of rescattering by free electrons during reionization, encoding the total optical depth along our line of sight. The 21-centimeter signal should shift in characteristic ways as spin temperature and ionization evolve, moving from absorption to emission depending on how the gas couples to radiation and to its own kinetic temperature. Yet the timeline remains uncertain, and that uncertainty is central to the mystery tone of this chapter, because the evidence is indirect and often integrated. We know ionization was largely complete by about 1 billion years after the beginning, but complete hides a complex geography of bubbles and islands. We do not know the exact start, the detailed pace, or the relative contributions of different sources across environments. Stars, galaxies, and accreting black holes may all play roles, and their balance is still debated, partly because each leaves overlapping signatures. The first galaxies are not yet the grand spirals of later epochs, and they do not resemble the calm, ordered disks familiar from nearby astronomy. They are small, merging systems embedded in growing dark matter halos, with irregular shapes and turbulent gas flows. Their star formation is bursty, regulated by feedback and by gas supply, and bursts can be followed by quiet intervals when gas is heated or expelled. They begin to assemble the larger families that will later dominate the cosmic web, and their mergers are both constructive and disruptive. Hierarchical growth continues as a background rule, and it ties the smallest scales to the largest architecture. Halos merge into larger halos, and baryons follow the gravitational bookkeeping, settling where the potential is deepest. Gas streams along filaments, feeding nodes where galaxies grow, and those streams can shock and heat as they collide. In this framework, the first stars are not isolated miracles, but early steps in a larger assembly line, and the assembly line is the cosmic web itself. Still, several unknowns remain stubborn, and they connect directly to the central question that runs beneath the narration. When exactly did the first stars ignite, and how quickly did they multiply once the first one succeeded? How massive were typical population 3 stars, and how often did they form in binaries or clusters rather than alone? How strong was feedback, and did it mostly suppress or trigger additional star formation in neighboring halos? And on what timescales did those effects propagate? Magnetic fields add another layer of uncertainty that is hard to constrain observationally because their signatures are subtle at high redshift. Were primordial fields strong enough to matter, or did amplification require later turbulence, driven by accretion and mergers? Did magnetically driven jets exist in the first protostars, and did they regulate accretion by clearing polar cavities? The answers affect fragmentation, angular momentum transport, and the masses of the first stars, and they also affect how quickly enriched gas mixes into the intergalactic medium. Even the chemistry has open edges, and those edges are not minor because they control cooling thresholds. How much H2 formed in typical mini-halos, and how often was it destroyed by early radiation fields that could travel far through a mostly transparent universe? Did HD cooling matter widely, or only in rare conditions where ionization and density favored it? How did shocks, turbulence, and streaming velocities alter reaction networks in real environments, where gas is not a uniform box but a chaotic flow? These uncertainties matter because they determine the first sources of heavy elements, and heavy elements determine the next era's star formation. The mass of a star determines whether it explodes, collapses, or disrupts completely, and each outcome leaves a different chemical signature. Pair instability supernovae, if they occurred, would leave distinctive abundance patterns with strong odd-even effects and large yields of certain elements. Finding those patterns in ancient stars is one way we test the story, because the oldest survivors carry the chemical memory of long-dead giants. The observational frontier is therefore forensic as much as direct, and it has grown through decades of increasingly precise instruments. We search for extremely metal-poor stars in the Milky Way halo as chemical fossils, measuring their spectra line by line to reconstruct early nucleosynthesis. We use deep field surveys to find galaxies near the rionization era and infer their star formation from faint, red-shifted ultraviolet light. We pursue 21-centimeter experiments to map neutral hydrogen statistically, even when imaging is impossible. And we treat foreground removal as a scientific challenge in its own right. New telescopes push the boundary, but the dark ages remain difficult by design because the universe at that time offers few photons to collect. The first stars are too distant and too short-lived to see directly in most cases, and their host halos are small and easily outshone by later structures. Their light is absorbed and redshifted, and much of the evidence arrives as integrated effects that demand careful modeling. Each inference is a bridge built from assumptions, and the strength of the bridge depends on how well we understand the underlying physics. Still, the narrative arc is firm enough to carry momentum, and it is anchored in processes we can test in other contexts. A neutral universe cools and gathers into halos, guided by dark matter scaffolding that shapes the cosmic web. Molecules enable further cooling, and collapse produces the first massive stars, which live fast and die loudly. Their radiation and explosions begin to reionize and enrich the cosmos, and those two changes, ionization and metals, reshape what can form next. This is the moment when nothing begins to look like something in the familiar sense, and the transformation is both visual and chemical. Light sources appear, and with them come heat, ionization, and chemical complexity, spreading outward through a medium that had been nearly uniform. The interstellar medium becomes an evolving ecosystem, rather than a passive reservoir, with feedback loops that can stabilize or destabilize future collapse. The universe starts writing new information into its own gas, patterns of temperature, composition, and ionization that did not exist before. The chapter returns to the documentary's central question without resolving it, because the first generation is where small-scale physics meets cosmic consequence. We can explain how gravity amplifies seeds and how cooling opens the path to stars, and we can simulate plausible histories. We cannot yet fully explain the detailed first generation because feedback, magnetism, and small-scale chemistry remain uncertain, and because the relevant objects are faint and brief. The first light is both a solution and a new set of puzzles, and the puzzles are the price of a universe that begins in darkness. We end by stepping from isolated ignition to collective architecture, because once stars exist, they rarely remain solitary for long. Once stars exist, they forge heavy elements and seed future cooling pathways, and those pathways allow new kinds of clouds to collapse. They assemble into galaxies that merge, grow, and trace the cosmic web's filaments, turning statistical fluctuations into visible structure. The long night breaks, and the next chapter follows the rise of early galaxies as structured families of light emerging from the last shadows of the Dark Ages. The universe does not build galaxies everywhere, and that absence is as important as the places where galaxies thrive. It builds them where the cosmic web concentrates matter, turning near uniform beginnings into a network of filaments, nodes, and expanding voids. Picture a vast, dark scaffold stretching across space, thin strands crossing like highways at night, with bright intersections where clusters will ignite. Between those strands, immense cavities open up, and the emptiness is not static. It grows as gravity pulls material away. After the first light and early enrichment, gravity keeps working in the dark, quietly amplifying tiny differences in density. Dark matter halos assemble and merge, and baryonic gas follows, because potential wells are the only stable addresses in an expanding universe. This preference is measurable in the statistics of structure. Small overdensities grow faster than their surroundings, and the growth rate depends on cosmic time, because expansion competes with gravitational attraction. On the largest scales, the cosmic web is the architecture, and it is remarkably consistent with the simplest cosmological models. Filaments act like channels, feeding nodes where halos grow into galaxies and clusters, while sheets and tendrils lace the space between. Voids expand between them, becoming emptier as matter drains toward denser regions, and their boundaries sharpen into walls. In simulations, voids look like bubbles pressed together, and the filaments are the seams where the bubbles meet. This web is not a decorative pattern, and it is not an artistic metaphor drawn over the sky. It is the late-time expression of the seed field measured in the CMB, amplified by gravity and shaped by expansion, dark matter, and dark energy. The CMB encodes those seeds as temperature and polarization variations at the level of tens of microkelvin. Those variations trace density perturbations, and the same spectrum of fluctuations later appears as the clustering of galaxies and the mass distribution inferred by lensing. Historically, this connection was a triumph of modern cosmology because it linked early universe physics to the visible universe. When surveys began mapping millions of galaxies, The emerging filaments looked uncannily like the structures predicted from CMB normalized initial conditions. Yet, even with that success, the web is not made of galaxies, and it is not made of gas alone. Most of its mass is dark matter, and the luminous parts are simply the places where ordinary matter managed to cool and condense. Galaxies begin as gas inside halos, but halos alone do not guarantee stars, and that distinction shapes the entire population. Gas must accrete, shock, cool, and lose angular momentum, or it remains hot and diffuse, glowing faintly in X-rays or not at all. The first step is accretion from the web, and it is not a gentle rain. Gas streams along filaments into halos, sometimes heating in shocks, sometimes arriving cold enough to penetrate deep, and both modes can occur in the same system. In a massive halo, infalling gas often crosses a virial shock near the halo boundary, where kinetic energy becomes heat. The gas can reach millions of degrees, and at those temperatures it radiates slowly, so it lingers as a hot atmosphere. In lower mass halos, or at earlier cosmic times when densities were higher, cold streams can survive longer. They thread through the hot medium like rivers through fog, delivering fuel directly to the inner regions where star formation can ignite. The balance depends on halo mass, redshift, and environment, and it also depends on how violently the halo has been stirred. A quiet halo can maintain coherent inflow, while a disturbed halo can shred streams through turbulence and mixing. Cooling is the gatekeeper that turns inflow into collapse, and it is a microscopic process with macroscopic consequences. Hydrogen and helium lines matter early, then metals and dust dominate once stars enrich the gas, and the cooling curve changes shape as chemistry becomes richer. At around 10,000 Kelvin, atomic hydrogen line cooling becomes efficient, allowing gas to shed energy rapidly. Below that, cooling can stall unless molecules or metals provide additional channels, which is why early star formation depends on the first sources of enrichment. Metals radiate through many fine structure and rotational transitions, and even trace amounts can matter. Dust grains add another pathway, because they absorb energy in collisions and re-radiate it in the infrared, quietly draining heat from dense regions. Cooling changes pressure support, fragmentation, and the pace of star formation, because colder gas has a smaller Jeans mass. In plain terms, when gas cools, it can break into smaller clumps, and those clumps can become the seeds of stellar clusters. As gas cools, rotation becomes unavoidable, and it is a consequence of cosmic geometry as much as local motion. Tidal torques from the web and nearby structures give halos angular momentum, and in falling gas settles into disks when it cannot fall straight in. Even a tiny sideways drift becomes important as collapse proceeds, because angular momentum is conserved unless it is transported. What begins as a subtle twist on megaparsec scales becomes a rotating disk on kiloparsec scales, and the disk's orientation remembers its accretion history. Disk formation is a compromise between gravity and angular momentum, and the compromise is never perfectly stable. Gas circulates in a flattened structure, then must transport angular momentum outward so mass can reach dense star-forming regions, and that transport is a central problem. Turbulence, gravitational instabilities, and magnetic stresses all help move angular momentum, and they do so in different regimes. Bars and spiral patterns can redistribute mass, while clumps migrate inward and build central concentrations, and the disk slowly rearranges itself. In a gas-rich disk, self-gravity can drive the tomb ray instability, breaking the disk into massive star-forming clumps. Those clumps interact, lose orbital energy, and drift inward, and the migration can build a bulge without a major merger. Magnetic fields add a quieter influence through magnetorotational and other instabilities, which can tap differential rotation. Even when the magnetic energy is small compared to gravity, magnetic tension can couple regions of the disk and alter how turbulence cascades. Mergers complicate every step, and they are not rare accidents in a hierarchical universe. Halos merge because hierarchical growth is built into the initial spectrum, and galaxies merge because they ride inside those halos, sometimes arriving with their own gas reservoirs. Some mergers are gentle, some are violent, and both leave long-term signatures that observers can still read. Tidal tails arc outward like luminous ribbons, stellar streams wrap around halos, and faint shells mark past collisions that ended long ago. Major mergers can destroy ordered disks and build spheroids because violent relaxation scrambles stellar orbits. They can also trigger starbursts by driving gas inward, compressing it rapidly, and feeding central black holes, which then respond with their own energy output. During a starburst, the star formation rate can jump by orders of magnitude for a short time, and the galaxy's light becomes dominated by young, massive stars. Dust often thickens in the same period, so the burst can glow brightest in infrared wavelengths, hidden from optical view. Minor mergers and repeated accretion can thicken disks, build stellar halos, and seed warps that persist for billions of years. They can also deliver fresh gas that restarts star formation after quiet periods, and they can perturb spiral structure without fully destroying it. Across these pathways, gravity is the organizer at every scale, but it is not the only actor. It assembles halos from the web, shapes disks through rotation and instabilities, and builds bulges through mergers and inward migration, while feedback and cooling decide what becomes visible. Within a forming galaxy, the interstellar medium becomes the decisive arena because it is where gas turns into stars. It is not a uniform gas reservoir, but a multi-phase system with its own cycles, thresholds, and memory, and its structure can change faster than the galaxy's orbit. The interstellar medium behaves like a weather system, and the analogy is more than poetic. Cold molecular clouds form stars, warm neutral gas fills much of the disk, and hot ionized bubbles expand after supernova and stellar winds, creating pressure fronts and cavities. In visuals, the ISM is a layered landscape, dark lanes of dust cutting across starlight, glowing nebulae outlining ionized regions, and faint, diffuse halos of hot gas rising above the disk. The galaxy's calm appearance hides constant motion, like an ocean seen from orbit. Cold molecular gas is dense and shielded, and it is where gravity can finally win on small scales. It collects in giant molecular clouds, where supersonic turbulence creates filaments and knots, and only the densest cores collapse into stars. Warm neutral and warm ionized phases occupy more volume, and they act as the background atmosphere of the disk. They respond to stellar radiation, shocks, and shear, and they can be stirred into fountains that rise and fall through the disk's gravitational field. Hot ionized gas, heated to millions of degrees, occupies the lowest density cavities and superbubbles. It can vent through chimneys into the halo, and those vents become the pathways through which galaxies breathe. Turbulence is the ISM's constant motion, and it is neither purely destructive nor purely supportive. It is driven by feedback, shear, inflow, and gravitational instabilities, and it both supports gas against collapse and creates dense pockets that can collapse. In a turbulent cloud, most of the gas is prevented from collapsing because random motions provide effective pressure. Yet turbulence also produces shocks, and shocks create temporary high-density regions, so turbulence can paradoxically trigger the very collapse it resists. Dust and metals change the rules of cooling and chemistry, and they are the galaxy's accumulated memory of past stars. Metals radiate efficiently. Dust shields molecules from dissociating radiation, and dust surfaces catalyze molecular hydrogen formation, which is otherwise slow in cold gas. This is why enrichment is not just decoration on a periodic table, but a control knob for star formation. A metal-poor ISM cools less efficiently, forms fewer molecules, and can remain more diffuse, while a metal-rich ISM can fragment readily and form stars in denser clusters. Every generation of stars rewrites the ISM, and it does so through multiple channels at once. Massive stars ionize and heat nearby gas, winds carve cavities, and supernovae inject energy, momentum, and newly forged elements, seeding the next cycle of chemistry. Supernova remnants expand as shock waves, sweeping up shells that can become sites of secondary collapse. Over time, overlapping remnants create superbubbles, and those superbubbles can punch through the disk, linking the ISM to the circumgalactic medium. Feedback is therefore not an afterthought, and it is not merely a correction in a model. It regulates star formation by preventing runaway collapse, but it can also trigger collapse by compressing shells and driving converging flows, which is why its net effect can be subtle. Radiation pressure from young stars can push on dust, especially in dense star-forming regions, and that pressure can help launch outflows. Photoionization heats gas and increases its pressure, and that heating can disperse clouds before they convert most of their mass into stars. The simplest picture is a loop, but the loop contains delays and thresholds that matter. Gas cools and forms stars. Stars inject energy and metals. The ISM changes phase and structure, and the next round of star formation inherits those conditions, not a blank slate. This loop is why galaxies can sustain star formation for billions of years, even though individual clouds live briefly. Inflow from the web replenishes gas, while feedback prevents the supply from turning into stars too quickly, and the galaxy hovers near a regulated state. Yet, the loop is not fully understood because feedback is multiscale and nonlinear. It begins in stellar atmospheres, couples to clouds, then to the disk, then to the halo, and sometimes to the intergalactic medium, and each coupling changes the outcome. A key uncertainty is how energy becomes momentum in a clumpy medium, because radiative losses can be severe. If a supernova explodes in dense gas, much of its energy can radiate away quickly, while the same explosion in a low-density cavity can drive a powerful, expanding shell. Outflows are one visible consequence of feedback, and they are easier to see than to interpret. Supernovae and radiation pressure can drive gas out of the disk, enriching the circumgalactic medium and reducing the fuel available for future stars, while leaving behind a disturbed, porous ISM. In spectra, outflows appear as blue-shifted absorption lines, and their velocities can reach hundreds or thousands of kilometers per second. In images, they appear as faint cones and filaments, glowing in emission lines as they collide with surrounding gas. Some outflowing gas escapes entirely, especially from small galaxies with shallow potential wells, and that loss can permanently reduce their star-forming capacity. Some falls back later as a galactic fountain, returning cooled material that can restart star formation, often at different radii. Black holes add another feedback channel, and their influence can be disproportionate to their mass. Accretion onto central black holes can launch jets and winds, heating halo gas and potentially preventing it from cooling back onto the galaxy, even when star formation is otherwise ready to resume. Jets can inflate cavities in hot gas, visible as bubbles in X-ray images of galaxy groups and clusters. Those cavities show that mechanical energy can be deposited far from the black hole, and they hint at how a small engine can affect a vast reservoir. This is one proposed route to quenching, and it is a central theme in galaxy evolution. A galaxy can stop forming stars if its gas is removed, heated, stabilized, or prevented from accreting, even while its stellar mass remains and its structure continues to evolve. Quenching is common, but its causes vary, and the same endpoint can hide different histories. Dense environments can strip gas through ram pressure, mergers can exhaust or heat gas, and massive halos can maintain hot atmospheres that cool slowly, starving the disk over time. In clusters, galaxies move through an intra-cluster medium, like ships through a dense sea, and the pressure can peel gas away. Tails of stripped gas trail behind, and star formation can shut down from the outside inward, leaving a red, aging disk. The circumgalactic medium sits at the boundary between Webb and galaxy, and it is both a reservoir and a filter. It stores inflowing and outflowing gas, mixes metals, and mediates how efficiently a galaxy can keep forming stars because it sets the conditions at the disk's edge. The CGM is tenuous and hard to image directly. So much of what we know comes from absorption lines in background quasars. Those lines reveal multiple phases, from cool, metal-bearing clouds to warm, hot, ionized gas, and they show that halos are dynamic, not static. The CGM is also where the cosmic web becomes local, and where the smooth becomes turbulent. Filamentary inflows can be disrupted by shocks, by feedback-driven turbulence, and by the changing pressure of a growing halo. And the inflow can arrive in bursts rather than steadily. In massive systems, the CGM can become a long-lived hot corona, supported by the halo's gravity and heated by accretion shocks. Cooling then happens through instabilities and condensation, and the question becomes whether cold clouds can form and survive long enough to feed the disk. Magnetic fields thread this entire system, even when they are hard to measure, and they add directionality to an otherwise chaotic medium. They influence cosmic ray transport, affect gas dynamics through magnetic pressure and tension, and modify how turbulence cascades, especially in diffuse plasmas. Magnetic fields can help support gas against gravity in some regions, while guiding collapse in others, depending on geometry and ionization. They can also shape outflows by collimating winds and altering how hot gas vents, turning a messy blowout into a more coherent flow. Cosmic rays are part of the same story, and they are an invisible pressure component that can travel far. They carry energy far from their sources, heat and ionized gas, and can contribute pressure that changes disk stability and wind launching, particularly in low-density regions. In some models, cosmic rays stream along magnetic field lines and excite waves that scatter them, coupling their momentum to the gas. That coupling can gently accelerate outflows over large distances, which differs from the more explosive push of thermal pressure alone. The origin and amplification of galactic magnetic fields remain active research, and the uncertainty is not a minor detail. Dynamos driven by turbulence and rotation can amplify weak seeds, but the timing and saturation levels are still debated, and early galaxies may have evolved under different magnetic conditions. Because these processes are coupled, galaxy formation is not a single pipeline, and it cannot be reduced to one controlling parameter. It is a competition between inflow and heating, between cooling and turbulence, and between collapse and disruption, with outcomes that depend on timing as much as strength. Despite that complexity, galaxies obey tight scaling relations, and the regularity is almost unsettling. Stellar mass correlates with rotation speed, size correlates with mass, and star formation rate tracks gas content with surprising regularity, as if galaxies are drawn toward preferred states. The Tully-Fisher relation links luminosity or stellar mass to rotation velocity, implying a connection between baryons and dark matter. The mass-metallicity relation links a galaxy's mass to its chemical enrichment, suggesting that outflows and retentions scale with gravitational depth. These relations are a clue and a challenge, and they shape how we interpret every observation. They suggest self-regulation that erases some history, yet they must emerge from messy processes that vary across environments and cosmic time, and that tension is the mystery. One mystery is why the relations are so tight, given the violence of mergers and the variability of accretion. If mergers, feedback, and inflow are chaotic, then galaxies should scatter more, unless hidden constraints force convergence, perhaps through equilibrium between supply and loss. Another mystery is how feedback truly couples to gas, especially in the multi-phase ISM, where densities vary enormously. Simulations must assume how supernova energy becomes momentum, how radiation interacts with dust, and how multi-phase gas mixes, and small differences can propagate into large outcomes. A third mystery is why some galaxies quench while others keep forming stars, even when their halos appear similar. Similar halos can host very different outcomes, implying that timing, environment, and internal structure matter, and that galaxies may cross irreversible thresholds. Unseen components may shape these pathways, and they remind us that our inventory is incomplete. Dark matter sets the gravitational scaffold, but its microphysics could alter small-scale structure, halo profiles, and the survival of thin disks, which would change how easily galaxies remain orderly. If dark matter is colder or warmer, more self-interacting or more granular, the number of small halos and the density of central regions can change. Those changes would ripple into merger rates, disk heating, and the resilience of dwarf galaxies, which are sensitive probes of the underlying physics. Dark energy changes the late-time growth of structure, and its influence is subtle but pervasive. As acceleration strengthens, the web's growth slows, inflow rates decline, and the universe becomes less efficient at building new galaxies, leaving existing systems to evolve more internally. Even the cosmological tensions echo here, because they touch the timeline of structure formation. If the Hubble tension or clustering tension reflects new physics, then the timing and efficiency of halo growth could shift, changing galaxy histories and the balance between early and late assembly. We reconstruct this story by combining observation and theory, and the partnership is essential. Observations provide snapshots across redshift, while theory supplies causal links that turn snapshots into an evolutionary sequence, and the two must be reconciled again and again. Deep field imaging reveals galaxies when the universe was young, and the images are time machines in plain sight. It shows that early galaxies are small, irregular, and rapidly evolving, consistent with frequent mergers and intense feedback, and their light is often clumpy and asymmetric. In those deep fields, the sky becomes crowded with faint smudges, each one a distant system seen in an earlier phase. Some appear as chains of bright knots, others as compact cores, and the variety hints at how quickly morphology can change during assembly. Spectroscopy adds the missing dimensions, and it turns pictures into physical diagnostics. Redshifts place galaxies in time, emission lines trace star formation and gas conditions, and absorption lines probe the CGM and intergalactic medium, revealing gas that would otherwise be invisible. Emission line ratios can indicate temperature, density, and ionization state, and they can reveal the presence of shocks or hard radiation fields. Line widths and velocity shifts can map rotation and turbulence, showing whether a galaxy is a settled disk or a disturbed merger. Gravitational lensing extends our reach, and it uses gravity as a natural telescope. It magnifies distant galaxies, maps dark matter in clusters, and measures halo masses without relying on light, which is crucial when baryons are faint or missing. Strong lensing can stretch a distant galaxy into arcs and rings, turning a tiny source into a resolved structure. Weak lensing, more subtle, statistically distorts background shapes, and from that distortion we infer the distribution of mass across the cosmic web. The 21-centimeter frontier promises a different view, one that follows neutral hydrogen directly. Mapping neutral hydrogen statistically could trace the web's gas supply, the growth of structure, and the transition from diffuse gas to galaxies, especially across the era when the first galaxies transformed their surroundings. Even without resolving individual galaxies, intensity mapping can reveal large-scale patterns in hydrogen emission. Those patterns can be cross-correlated with galaxy surveys, offering a way to connect the luminous population to the underlying gas reservoir that feeds it. Theoretical astrophysics builds the counter-narrative in silicon, and it is a controlled experiment the universe does not allow us to run. Simulations start from CMB consistent initial conditions, evolve dark matter and gas, and attempt to reproduce the observed galaxy population, including its diversity. But simulations face a scale problem, and it is a fundamental limitation rather than a minor inconvenience. Star formation and supernova remnants are small, while galaxies and filaments are vast, so models use subgrid physics to approximate unresolved processes, and those approximations matter. A single star-forming region can be parsecs across, while a cosmological simulation volume can be hundreds of megaparsecs wide. The gap spans many orders of magnitude, and bridging it requires recipes that compress complex physics into a few parameters. Feedback prescriptions are therefore both essential and uncertain, and they are often the difference between success and failure. Different choices can produce different galaxy morphologies, star formation histories, and metal distributions, even with identical initial conditions, because feedback sets the efficiency of conversion. This is why the same beginning can yield diverse shapes, and why diversity does not necessarily mean randomness. Spirals, ellipticals, and irregulars may arise from different merger histories, gas fractions, feedback strengths, and angular momentum retention, and the web supplies each system differently. Spiral structure itself is a gravitational pattern, and it can be long-lived or transient depending on conditions. Density waves, transient arms, and bar instabilities can organize stars and gas, while also driving inflow that builds central bulges, and the arms become both signposts and engines. In a spiral arm, gas compresses as it enters the pattern, triggering star formation along ridges that glow in blue starlight and pink emission lines. Downstream, supernovae and winds disperse the clouds, leaving behind associations of young stars that drift away as the pattern continues. Bulges can form through mergers, but also through secular evolution, and the distinction can blur in real galaxies. Repeated internal instabilities can thicken the central region, blurring the line between violent and gradual formation, and leaving mixed stellar populations. Ellipticals often reflect a history of mergers and quenching, and their smooth light hides a turbulent past. Their stars can be old, their gas poor, and their halos massive enough to maintain hot atmospheres and suppress cooling, so they evolve mostly through stellar aging and minor accretion. In clusters, ellipticals dominate the dense cores, and their environments are rich in hot gas and frequent interactions. The setting itself becomes part of the explanation, because the web's nodes are where both mass and heating accumulate. Dwarf galaxies expose the limits of our understanding, and they are disproportionately informative. They are sensitive to feedback, reionization, and environment, and they test whether dark matter behaves as expected on small scales, because small changes can erase or preserve them. A burst of star formation can blow out much of a dwarf's gas, and the same event in a larger galaxy would be a minor disturbance. Reionization can heat intergalactic gas and prevent it from accreting onto small halos, leaving some dwarfs starved before they truly begin. Across all masses, the cosmic web remains the supply chain, and it is never fully switched off. Filaments feed halos, halos feed galaxies, and galaxies feed back into their surroundings through winds and enriched outflows, and the cycle links the smallest scales to the largest. The central question returns with sharper stakes, because it is both physical and philosophical. How did near-uniform beginnings produce a universe of structured cities of stars? And why does the outcome look both diverse and strangely constrained, as if governed by hidden balances? We can explain the broad outline with gravity, cooling, and feedback, and that outline is robust across models. We still struggle to predict the detailed demographics, the tight relations, and the precise mechanisms that regulate growth, especially when small-scale physics shapes large-scale outcomes. The story is therefore both solved and unfinished, and that tension is what keeps the field alive. Galaxies are not isolated islands, but nodes in a living web, and their internal weather is tied to the universe's largest anatomy, even when the connection is hard to see. Transition. From the general story of galaxy formation, we zoom into one particular galaxy, our own, and ask what its structure reveals about broader rules. We zoom into one galaxy to test the universe's rules against a familiar sky, and the view tightens until the Milky Way fills the frame. The Milky Way is not a special exception, yet it is our only close laboratory, where we can count stars one by one. From outside, it would look like a barred spiral, a luminous pinwheel with dusty lanes stitched across its arms. From within, it is a sky-wide river of light, brightened by billions of suns and dimmed by soot-like grains. Its basic architecture is simple in outline and complex in detail, like a skeleton wrapped in weather. A thin, rotating disk holds most gas, dust, and young stars, and it is where the galaxy still feels alive. A thicker disk and central bulge hold older populations and hotter motions, preserving a record of earlier upheavals. A faint halo surrounds everything, built from ancient stars and dark matter, extending far beyond the visible glow. The disk is where ongoing star formation writes the newest chapters, and the visuals are almost tactile. In infrared, warm dust outlines spiral structure like embers in a slow whirl. In radio maps, hydrogen gas spreads in broad sheets, then gathers into knots where gravity gains purchase. In optical light, bright blue clusters mark recent births, while dark lanes cut across them like ink. Spiral arms are not rigid structures, but patterns that compress gas as it orbits, more like traffic jams than solid walls. Stars and clouds move through the pattern, speeding up and slowing down under the galaxy's gravitational potential. As gas enters an arm, it is squeezed by shocks and converging flows, and that compression can push clouds over the threshold for collapse. Feedback then disrupts clouds and reshapes the next cycle, so the arms become both signposts and engines. The physics of that compression is deceptively subtle because the disk is not a smooth fluid. Supersonic turbulence, self-gravity, and shear from differential rotation all compete, and the outcome depends on local conditions. In some regions, gas piles into giant molecular complexes, hundreds of light years across, with internal filaments like braided rope. In others, the arm passage only triggers modest clumps that disperse before they can form many stars. The spiral pattern links rotation to birth, but it does not dictate a single fate. The bulge marks a different environment and a different history, and the camera would feel the pace change. The starlight grows denser and redder, and the orbits become less like lanes on a highway and more like a stirred swarm. Its stars are generally older and more metal-rich than the halo's oldest survivors, implying long periods of early star formation and rapid chemical recycling. Its motions are less orderly, suggesting violent early assembly and later rearrangement, including the growth of a bar that funnels gas inward. At the very center sits a compact radio source, Sagittarius A, a supermassive black hole with about 4 million solar masses. It is small on the sky, yet it dominates the dynamics within its immediate neighborhood. When we speak of a black hole, we mean an event horizon where escape becomes impossible. But the spectacle comes from the surrounding plasma. Gas heats to extreme temperatures as it spirals inward, and magnetic fields twist into knots, launching flares that briefly brighten the darkness. The halo is the Milky Way's memory, scattered into streams and clumps that arc across the sky in faint, ghostly bands. Stellar streams trace disrupted dwarf galaxies and globular clusters, stretched by tides into long ribbons that wrap the galaxy like loose threads. Their chemistry and motions record when mergers happened and how much mass they carried, because each infalling system had its own enrichment history. The halo's globular clusters are time capsules, but even they show multiple populations and complex formation, hinting at dense, early environments. Dark matter is the halo's unseen scaffolding, inferred from motion rather than light. The outer disk rotates too fast to be held together by visible stars and gas alone, so an extended mass component must be present. Rotation curves, plots of orbital speed versus radius, stay flat where they should fall, and that mismatch is one of modern astronomy's most persistent clues. In simulations, dark matter halos form first, then pull in baryonic gas, setting the stage for disks, bulges, and satellites. Stellar populations act as a fossil record of galaxy formation because stars preserve the chemical state of the gas they formed from. Population. Stars in the disk are young and metal-rich, shaped by many enrichment cycles and continual mixing. Population 2, stars in the thick disk and halo are older and metal-poor, closer to early cosmic chemistry and early star formation conditions. The rarest ultra-metal-poor stars preserve signatures of the first supernovae, even when the first stars themselves are gone. Those signatures are not poetic metaphors, but measurable patterns in spectra. When starlight is split into a rainbow, dark absorption lines reveal specific elements, and their relative depths encode abundance ratios. Some ratios point to core collapse supernovae, which enrich quickly with oxygen and magnesium. Others suggest type Ia supernovae, which arrive later and add iron, shifting the chemical fingerprint over time. In this way, chemistry becomes a clock, imperfect but powerful. This fossil record connects directly to the central question because it ties local structure to the universe's earliest conditions. The CMB's tiny seed pattern grew into halos, then into mergers, then into a settled spiral, and each stage left traces. The Milky Way is one outcome of that amplification, constrained by gravity and by the universe's expansion history. Yet the origin of the seeds still hides behind the observational curtain, and we can only infer it through consequences. The Milky Way's present shape also reveals its merger history, and Gaia has turned that history into a map. Gaia's astrometry measures positions, distances, and proper motions for more than 1 billion stars, and the result is a 6-dimensional view of phase space. In that space, coherent groups stand out like schools of fish in a turbulent sea. Debris from major accretion events remains visible as kinematic clumps even after the stars have spread across the sky. The Gaia sausage and other features imply a significant merger that heated the early disk and puffed it into a thick component. That event likely happened billions of years ago, when the galaxy was still assembling and gas was more abundant. Smaller satellites continue to fall in, building the halo and stirring the outer disk, and some are still visible today. The Sagittarius dwarf galaxy, for example, is being torn apart in real time, leaving a stream that loops around us. Mergers do more than add stars, because they also rearrange gas and angular momentum. A collision can drive gas inward, feeding central starbursts and possibly black hole activity. It can also warp the disk, leaving ripples and vertical waves that persist for hundreds of millions of years. When we see the Milky Way's disk bending like a shallow S-shape, we are likely seeing the afterimage of gravitational encounters. The galaxy is not static. It is still settling. The galaxy is not only stars, but an interstellar medium that behaves like an ecosystem, with cycling and feedback. Gas exists in multiple phases that exchange mass and energy, and those phases are interleaved rather than neatly separated. Cold molecular gas forms stars, warm neutral gas fills much of the disk, and hot ionized gas occupies bubbles and chimneys that vent into the halo. These phases are coupled by shocks, radiation, turbulence, and gravity, so changes in one phase echo through the rest. Molecular clouds are the immediate reservoirs for star formation, and they are visible as dark silhouettes against the Milky Way's glow. They are cold, dense, and dusty enough to shield molecules from dissociating ultraviolet light, allowing carbon monoxide and more complex species to persist. Typical temperatures can be only 10 to 20 Kelvin, meaning atoms move slowly and can stick to grains. Yet the clouds are not calm, because turbulence stirs them into filaments, sheets, and knots. Within those clouds, self-gravity selects the densest pockets for collapse, but only a small fraction actually becomes stars. The star formation efficiency is low, implying regulation rather than free fall, and that regulation has several suspects. Turbulence can provide transient support, magnetic fields can resist compression, and feedback can blow cavities that halt accretion. Even the cloud's environment matters, because spiral shocks and nearby explosions can either trigger or shred it. Ionized regions mark where massive stars have already turned on, and they announce themselves with a different palette. Ultraviolet photons carve H2 bubbles that expand into surrounding gas, and in narrow band images, they glow in pink and violet emission lines. These regions can compress nearby material and trigger secondary collapse, or they can disperse clouds and halt accretion. The same feedback can both create and destroy nurseries, depending on geometry, density, and timing. Supernovae add another layer of feedback, injecting energy and freshly forged elements into the surrounding medium. A single explosion can drive a shock wave for tens of parsecs, sweeping up gas into shells where new clouds may form. In hot cavities, the gas becomes tenuous, and million-degree plasma emits X-rays, tracing the aftermath. Over time, overlapping supernova remnants can create superbubbles that punch through the disk. These chimneys help circulate metals into the halo, making enrichment a galactic-scale process. Dust lanes trace both chemistry and dynamics, and they are more than mere obscuration. Dust absorbs starlight and re-radiates in infrared, turning hidden star-forming regions into bright thermal beacons. Dust also catalyzes molecule formation on grain surfaces, especially molecular hydrogen, which is otherwise hard to assemble in the gas phase. Grains carry electric charge and couple to magnetic fields, affecting how gas cools and fragments. Dust is also a tracer of spiral shocks and bar-driven inflow, revealing where gas is being funneled inward. Star formation today is not identical to star formation in early epochs, and the difference is written into the universe's timeline. Early galaxies were more gas-rich, more turbulent, and more merger-driven, so their disks were thicker and more chaotic. Metallicity was lower, changing cooling pathways and the mass scale of fragmentation, which likely altered the typical mass of newborn stars. Feedback operated in denser environments, and the balance between inflow and outflow differed, sometimes producing powerful galactic winds. When we look at distant galaxies, we are watching that earlier regime in action. In the Milky Way, we can compare these regimes by reading gradients and ages, like layers in a geological outcrop. The inner disk is more metal-rich, reflecting faster enrichment and stronger recycling, and its stars show a broader range of chemical histories. The outer disk is more metal poor, and more sensitive to accretion from the circumgalactic medium, where fresh gas can dilute metals. The thick disk suggests an earlier era of hotter dynamics and rapid formation, perhaps during a time of intense star formation and mergers. Those gradients are not perfectly smooth because the disk mixes itself. Stars migrate radially over time, exchanging places through resonances with spiral structure and the bar. Gas flows inward and outward, and fountains launched by supernovae rain back down in different locations. As a result, the Milky Way's chemical map is a palimpsest, overwritten but not erased. What looks like a simple metallicity slope hides countless individual histories. The interstellar medium is threaded by magnetic fields that are hard to see directly, yet they leave fingerprints in light. We map them through polarization of starlight and dust emission because elongated grains align with field geometry and preferentially absorb or emit certain orientations. We also use Faraday rotation, where magnetized plasma twists the polarization of background radio waves, and the amount of twist depends on electron density and field strength. Together, these methods reveal large-scale coherence and small-scale turbulence, like a weather map for invisible forces. Magnetic fields shape gas flows even when magnetic energy is not dominant, because they can redirect motion and change how instabilities grow. Magnetic pressure and tension can support diffuse gas and guide collapse along preferred directions, producing filaments aligned with field lines. Fields influence how turbulence cascades, how shocks propagate, and how cosmic rays travel through the disk. In molecular clouds, field geometry can affect filament formation and the efficiency of core collapse, subtly changing the stellar initial mass function. Magnetism also affects angular momentum transport, which is a recurring obstacle in forming compact objects. In rotating disks, magnetorotational instability can drive turbulence that redistributes angular momentum, allowing gas to drift inward. In protostellar systems, magnetic braking and magnetically launched outflows can remove angular momentum from infalling gas, preventing it from piling up at large radii. These processes help explain why stars form at all, despite the tendency of rotation to halt collapse. They also connect the Milky Way's large-scale magnetism to the smallest scales of planet formation. Yet the Milky Way's magnetic ecology still contains open questions, and they are not minor details. We do not fully know the origin of the seed fields that dynamos amplify, whether they arose from early plasma processes or from the first generations of stars. We do not fully know how quickly fields grew in early galaxies, or how saturation depends on feedback and gas accretion. We also do not fully know how magnetic reconnection and diffusion operate in a multi-phase medium, where cold clouds sit inside hot plasma. The field is everywhere, but its history remains partly hidden. The galaxy's center is an extreme environment that tests these ideas, and it looks like a different world. Sagittarius A is quiet today, but it likely flared in the past, and the evidence is written in energetic structures. Giant lobes of gamma-ray and microwave emission rise above and below the plane, suggesting past outbursts or sustained winds. X-ray echoes in nearby molecular clouds hint at earlier bright phases, as if the clouds are reflecting ancient light. The central molecular zone is dense and turbulent, forming stars under higher pressure and stronger tidal forces. In that central zone, clouds can be squeezed to densities rare in the outer disk, yet star formation appears oddly inefficient. Shear, turbulence, and magnetic fields may keep gas from settling into long-lived cores, delaying collapse. When collapse does happen, it may favor massive clusters, producing intense feedback in a compact region. The center, therefore, becomes a stress test for our models because it pushes every parameter to an extreme. It also reminds us that a galaxy contains many climates, not one. Galactic environment matters for habitability in ways that are still debated because life depends on both chemistry and stability. The inner galaxy has higher stellar density and higher radiation backgrounds, and close stellar encounters are more frequent. Supernova rates and cosmic ray fluxes vary with radius and with time, and those changes can alter atmospheric chemistry. Metallicity also varies, changing the availability of rocky planet-building material and perhaps the frequency of giant planets. The question is not whether environment matters, but how strongly it filters outcomes. A proposed galactic habitable zone is therefore plausible but uncertain, because the constraints pull in opposite directions. Too few metals can limit rocky planets and complex chemistry, and it can also slow the formation of solid cores. Too much radiation and too many nearby explosions can strip atmospheres or disrupt biospheres, especially on planets without strong shielding. The Milky Way's history suggests that habitability is not a single location, but a moving window in space and time. As the galaxy enriches and calms, the window may widen. From this galactic scale, we bridge to a local story that still follows universal rules, and the camera drops toward one ordinary star. The solar system formed from the same processes that build disks around young stars everywhere, and its uniqueness is not assumed. It is a small eddy in a larger flow, shaped by gravity, rotation, chemistry, and time. The same equations that describe spiral shocks also describe the collapse of a single core, just with different units. The key prerequisite was enrichment by previous generations of stars, because the early universe began almost chemically blank. Primordial nucleosynthesis made mostly hydrogen and helium, with only trace lithium, and that composition persisted for hundreds of millions of years. Everything heavier was forged later in stellar cores and supernovae, and then mixed into the interstellar medium through winds and shocks. Without that enrichment, there would be no silicates, no iron cores, and no complex organic chemistry. Even water, so central to habitability, requires oxygen made in stars. The sun's birth cloud was therefore not pristine, and its dust carried a long ancestry. It contained metals and dust from many earlier lives, including elements made in different astrophysical sites and released on different timescales. Carbon and oxygen are built in stellar interiors and distributed by winds and explosions, while nitrogen has its own pathways in intermediate mass stars. Iron group elements are made in supernovae, while many heavy nuclei require neutron-rich environments, such as rapid neutron capture in extreme events. The periodic table is a map of astrophysical processes, not a single factory. One mystery is how local that enrichment was, and the clues come from isotopes that decay quickly. Some evidence suggests a nearby supernova injected short-lived radionuclides into the forming system, leaving a measurable excess in meteorites. Isotopes like aluminum-26 imply a recent nucleosynthetic event close enough to seed the disk, because its half-life is only about 700,000 years. The exact source could be a supernova, a massive star wind, or a combination within a clustered nursery. Each possibility implies a different birth environment for the Sun. Those radionuclides mattered because they provided heat inside early planetesimals, driving melting and differentiation. In the first few million years, aluminum-26 decay could turn small bodies into miniature worlds with metallic cores and volcanic surfaces. That internal processing affects how water and organics are stored or lost, and it shapes the building blocks that later assemble into planets. A seemingly minor isotopic detail becomes a lever on planetary geology. It also ties a rock in a museum to an explosion in deep time. The solar system's formation begins with collapse of a dense core in a molecular cloud, and the visuals shift to a cold, dark cradle. Gravity pulls inward, but angular momentum forces material into a rotating disk, flattening the infall like batter spun in a bowl. The protosun forms at the center, accreting mass through the disk, while the outer disk remains cool and dusty. Jets and outflows likely remove angular momentum and regulate accretion, carving bipolar cavities that glow in shocked emission. Even at birth, the system is already shaping its surroundings. In the disk, dust grains collide and stick, building larger aggregates in a process that begins almost invisibly. Growth proceeds from micron grains to pebbles, then to planetesimals that can gravitationally focus more material, accelerating their own growth. Accretion becomes runaway for the largest bodies, producing protoplanets that dominate their neighborhoods. The process is efficient but not perfectly understood, especially across the meter-size barrier where drift and fragmentation compete. Somewhere in that barrier, the difference between a dusty disk and a planetary system is decided. Modern models add nuance by invoking streaming instabilities, where pebbles concentrate into dense filaments that collapse under their own gravity. In that picture, planetesimals can form rapidly, bypassing some of the slowest steps of sticking. Observations of protoplanetary disks support this complexity, showing rings, gaps, and spirals even around very young stars. Those structures may be carved by forming planets, or they may arise from pressure bumps and magnetic effects. Either way, the disk is not a featureless pancake. It is a dynamic laboratory. Temperature gradients in the disk set chemical boundaries, and those boundaries are visible as invisible lines of condensation. Inside the snowline, water ice is unstable, and solids are mostly rocky, limiting the mass available for rapid growth. Beyond it, ices add mass and allow faster core growth, favoring giant planet formation and the retention of volatiles. These boundaries shift with time as the young sun brightens and the disk evolves, so the chemistry of a planet depends on when and where it assembled. A planet's composition is therefore a time-stamped coordinate. Giant planets likely formed early, before the gas disk dispersed, because they require abundant hydrogen and helium. Their cores accreted gas envelopes, becoming Jupiter and Saturn, and their gravity then shaped the rest of the system by stirring planetesimals and sculpting resonances. Their formation also influenced the delivery of volatiles to the inner planets, either by scattering icy bodies inward or by blocking certain pathways. The giants are not just large planets, but architects of the system's final layout. Their presence turns a disk into a structured hierarchy. Planet migration is a central part of modern formation theory, and it reframes how we interpret the solar system's order. Interactions with the gas disk can move planets inward or outward on short timescales. because gravitational torques exchange angular momentum with the disk. Later, gravitational interactions among planets can rearrange orbits after the gas is gone, producing instabilities that scatter bodies and reshape belts. Migration explains many exoplanet systems, including hot Jupiters and compact chains of super-Earths. The solar system's exact migration history remains debated, which means its apparent stability may hide a turbulent youth. The inner planets formed from rocky material in a region repeatedly heated and depleted, and the visuals become violent and bright. Collisions built Mercury, Venus, Earth, and Mars through a chaotic sequence of impacts, with each collision converting orbital energy into heat. Some impacts were gentle mergers, while others were catastrophic, stripping mantles and vaporizing oceans of magma. The Moon likely formed from a giant impact, leaving a chemical and dynamical fingerprint in isotopes and angular momentum. Late accretion delivered additional material recorded in cratered surfaces and isotopic ratios, and it may have influenced early atmospheres. Leftover debris remains as a signature of incomplete assembly, and it still circles the Sun like a fossil ring. The asteroid belt is not a failed planet so much as a region stirred by Jupiter's gravity, where resonances increase collision speeds and prevent quiet growth. The Kuiper belt preserves icy remnants beyond Neptune, shaped by resonances and scattering, and its objects retain primitive ices and organics. Comets and small bodies act as time capsules, preserving chemistry from the early disk in cold storage. When they fall inward, they deliver that record to telescopes and spacecraft. This local narrative connects back to the Milky Way's interstellar medium because the solar system is made of recycled galactic material. The Sun formed in a star-forming region, likely with siblings in a cluster, and that cluster would have shared a chemical fingerprint. Those siblings dispersed into the disk, becoming hard to identify after billions of years because orbital mixing scrambles their paths. Finding them would link a planetary system to a precise galactic birthplace, turning a family story into a measurable dataset. It is a reminder that even our origin has a larger address. Now we connect cosmic history to life without assuming life is inevitable, and the tone becomes more cautious. Life requires chemistry that the early universe did not provide, and it requires environments that remain stable for long spans. It requires stable environments that are rare in violent early epochs, when radiation fields were harsher and impacts more frequent. It requires time, because complexity builds through long sequences of selection and contingency, and those sequences can be interrupted. The universe had to mature before it could even attempt biology. A minimal habitability checklist is straightforward in principle, even if difficult in practice. Liquid water is a powerful solvent and a marker of moderate temperatures and pressures, and it enables rich chemistry in a mobile medium. Energy sources are required, from sunlight, chemical gradients, or geothermal heat, because metabolism needs a sustained push away from equilibrium. Stable conditions are needed long enough for complex systems to persist and adapt, which means stability across seasons, epochs, and sometimes geological eras. The checklist sounds simple, yet each item hides many unknowns. Chemical complexity is the deeper requirement that ties biology to cosmology because it depends on stellar history. Life needs carbon-based frameworks, but it also needs nitrogen, oxygen, phosphorus, sulfur, and trace metals that act as catalysts. These elements are not primordial, so biology depends on stellar nucleosynthesis and recycling, and on the mixing that spreads those products through galaxies. The universe had to age into habitability, turning simple gas into a chemically rich medium, and that aging is measurable in metallicity. In a sense, life is downstream of the first stars. Planetary habitability is not only about distance from a star, because planets are systems with feedback. Atmospheres regulate temperature through greenhouse effects and circulation, and they can buffer a planet against changes in stellar output. Magnetic fields can shield atmospheres from stellar wind stripping, though their necessity is debated and may depend on atmospheric composition and replenishment. Plate tectonics and geochemical cycles may stabilize climate by regulating carbon dioxide, but we do not know how common such cycles are. Even on Earth, stability is a negotiated truce between geology, oceans, and air. The sun provides a relatively steady energy source, but it is not perfectly constant, and early conditions were harsher. Young stars are more active, with flares and stronger winds that can erode atmospheres and alter surface chemistry. Stellar variability and high-energy radiation can both hinder and drive chemistry, breaking molecules, but also enabling new pathways. Habitability may require a balance between stability and stimulation, where chemistry is energized without being sterilized. That balance is not a single number, but a moving target over time. The galactic environment adds another layer of risk and opportunity because a planet does not orbit in isolation. Nearby supernovae can bathe planets in radiation and alter atmospheres, and they can also compress clouds and trigger new star formation. Gamma-ray bursts are rarer but potentially catastrophic at close range, and their beaming makes them unpredictable hazards. Dense regions increase encounter rates that can perturb comet reservoirs and raise impact hazards, changing the long-term bombardment rate. The same galaxy that provides heavy elements also supplies occasional threats. Metallicity links galaxy evolution to planet formation, and the relationship is more nuanced than a simple threshold. Higher metallicity increases the solid material available for building rocky planets and the cores of giants. And surveys show giant planets are more common around metal-rich stars. Yet very high metallicity may also favor giant planets that migrate and disrupt inner systems, changing the odds for stable terrestrial orbits. The relationship between metallicity and Earth-like outcomes is therefore not monotonic and not settled. The galaxy's chemical evolution sets the stage, but it does not write the script. Exoplanet surveys have changed the stakes by showing that planets are common, and the visuals widen to a sky full of dots. Kepler and follow-up studies imply that small planets are abundant around many stars, and that multi-planet systems are typical rather than rare. Yet Earth size does not guarantee Earth conditions, and we still lack atmospheric data for most candidates, especially at Earth-like temperatures. The most important unknown is not whether planets exist, but how many are truly habitable. The census is large, but the diagnoses are few. We also face a detection problem that echoes the documentary's theme, because absence of evidence is not evidence of absence. The universe can be full of life and still appear silent if signals are rare, brief, or not aimed at us. Technosignatures may be uncommon, or they may be hard to distinguish from natural phenomena, especially across interstellar distances. Biosignatures may be subtle, context-dependent, and vulnerable to false positives and false negatives, requiring careful interpretation. The quiet sky may be a limitation of our instruments, or a clue about rarity. This uncertainty is the modern form of an older mystery, and it has a history of its own. The Drake equation frames the factors, but most terms remain poorly constrained because we have only one confirmed example of life. Biology may be common once chemistry and water align, or it may require rare steps like the origin of replication and the emergence of complex cells. Intelligence and technology may be even rarer or simply transient, rising and falling on timescales too short for easy overlap. The equation organizes ignorance, and that is part of its value. The Milky Way becomes the arena where these probabilities play out, because it is both vast and knowable in detail. It contains hundreds of billions of stars and a long history of chemical enrichment, and it has hosted many cycles of star birth and death. It also contains hazards that vary across time, including bursts of star formation and central activity that can raise radiation backgrounds. Our existence proves possibility, but it does not reveal frequency, and that gap is where mystery lives. The galaxy is large enough for many outcomes, including rare ones. We return to the central question with new weight, because the chain now includes both physics and biology. How did near-uniform beginnings produce a galaxy that can host complex chemistry and living observers? And why did it happen here at all? The same physics that amplifies tiny seeds also creates the conditions for biology, but only after long delays and many contingencies. The path from the CMB's microkelvin ripples to a habitable planet is continuous, yet it is not guaranteed. Continuity does not imply inevitability. Mysteries remain at every link in the chain, and the unanswered parts are as important as the known ones. We do not know the Milky Way's full merger history, especially in the earliest epochs, when the evidence is hardest to preserve. We do not know the detailed role of magnetic fields in regulating star formation across cosmic time, or how they interact with feedback in different environments. We do not know how typical the Sun's birth environment was, or how often enrichment events seed disks with key radionuclides. Each uncertainty is a doorway to a deeper model. We also do not know the distribution of Earth-like worlds in the galaxy, because we are only beginning to measure atmospheres and surfaces. We do not know how often stable climates persist for billions of years, or how often planets avoid runaway greenhouse or deep freeze. We do not know how often life begins, or how often it survives planetary and stellar upheaval, including impacts and stellar evolution. The silence could mean rarity, or it could mean our methods are still crude. It could also mean that life is common but quiet. This chapter's climax is a reversal of perspective, and the visuals should feel like a slow pullback. The Milky Way is not just our home, but a visible cross-section of cosmic evolution, suspended as a luminous disk within a dark halo. Its disk, bulge, and halo are the grown-up form of early fluctuations, shaped by mergers, feedback, and time, and still changing today. The solar system is a local condensation of that history, built from recycled stardust and shaped by migration and impacts. In that condensation, chemistry found a stable niche long enough to become curious. Transition. To answer how we know any of this, and what still resists explanation, we pull back to the tools and theories that probe the deepest questions, including expansion itself. We end where the story began, at the uncomfortable edge of nothing and first causes, where explanation thins and language starts to fail. The central question remains practical and profound, because it is also a question about method. How did galaxies and worlds form from near uniform beginnings, and what still blocks a complete explanation? We know this history because astronomy is now a forensic science across time, built from faint traces and careful inference. Light is delayed information, and distance becomes a look-back clock, so every telescope is also a time machine. When a spectrum arrives, it carries the imprint of atoms, dust grains, and plasma, each leaving a recognizable signature. Every measurement is a compromise between what the universe emits and what our instruments can recover, and those compromises shape what we think we know. The modern toolkit starts with multi-wavelength surveys that treat the sky as layered evidence, like transparent sheets stacked into a single scene. Radio traces cold hydrogen through the 21-centimeter line, and it also reveals synchrotron electrons spiraling in magnetic fields. Infrared reveals dust warmed by starlight, turning opaque clouds into glowing maps of hidden star formation. Optical maps stars and galaxies in bulk, where morphology and color hint at age, metallicity, and environment. Ultraviolet and X-rays expose hot gas, shocks, and accreting black holes, where gravity converts infall into heat and radiation. Each band corrects the other's blind spots, because the universe hides itself differently at each energy, and it rarely tells the whole story in one color. Dust blocks optical light but glows in infrared, so a quiet-looking spiral can conceal a starburst in its core. Hot plasma is invisible in narrow radio lines but bright in X-rays, outlining cluster atmospheres and supernova-heated bubbles. The same galaxy can look calm in starlight and violent in high-energy emission, as if two histories overlap in the same place. Surveys also become statistical, because cosmic history is written in populations, not anecdotes, and the universe is too large for hand-picked examples. We map millions of galaxies to measure clustering, bias, and environment, then compare those patterns to the fingerprints of early fluctuations. We use weak lensing to weigh the cosmic web without relying on light, reading tiny, coherent distortions in background galaxy shapes. We cross-correlate maps to reduce systematics and expose shared structure, because agreement across instruments is its own kind of evidence. Time domain astronomy adds a second axis, because the sky is not static, and change is often more informative than brightness. Supernovae mark stellar deaths and calibrate distances through standardizable candles. After their light curves are corrected for color and stretch, variable stars trace stellar evolution and anchor the local distance ladder, because their periods encode their intrinsic luminosities. Transients reveal compact objects, tidal disruptions, and the growth of black holes, brief flares that turn otherwise invisible engines into measurable physics. Precision cosmology turns these data into parameters, but the parameters are not the point, and they never replace the underlying story. We measure the expansion history through redshift and distance relations, watching spectral lines slide as space itself stretches. We infer matter content from CMB anisotropies, BAO, and lensing, combining early universe relics with late-time structure. We test growth of structure through clustering and redshift space distortions, where peculiar velocities compress and stretch patterns along the line of sight. Distance measurement is the backbone, and it is built as a ladder with overlapping rungs, each one checked against the next. Parallax sets the geometric base for nearby stars, using Earth's orbit as a baseline and milliarc second shifts as a ruler. Cepheids and other variables extend the scale to nearby galaxies, and their calibration depends on metallicity and crowding in dense fields. Type Ia supernovae push to cosmological distances where expansion dominates the signal, and the universe's acceleration becomes visible in the residuals. Independent methods check the latter, because calibration errors can mimic new physics, and cosmology is unforgiving about small biases. BAO provides a standard ruler tied to early universe sound waves, frozen into galaxy clustering when photons decoupled from baryons. Time delays in strong lensing offer another route to H0, because multiple images follow paths with different geometric and gravitational delays. Gravitational wave sirens promise distances without a traditional ladder if counterparts or statistical hosts are identified and selection effects are controlled. These tools reconstruct a timeline, but reconstruction is not the same as witnessing, and the difference matters at the edge of the observable. We infer the early universe through relics, not direct images, and relics can be interpreted in more than one way. The CMB is the oldest light, but it is also a wall, because before recombination, the universe was an opaque plasma. Behind it, we must rely on consistency between theory and later structure, and on subtle signatures embedded in polarization and lensing. Transition. To understand what the data mean, we move from telescopes to equations and simulated universes. Theoretical astrophysics is the bridge from laws to outcomes, and it is where assumptions become visible because they must be written down. We start with gravity, expansion, and initial conditions consistent with the CMB, including a specific spectrum of primordial fluctuations. We evolve dark matter into halos and filaments, forming the cosmic web through hierarchical merging and tidal interactions. We add baryons, cooling, chemistry, star formation, and feedback, then compare to observed galaxies with the same statistical discipline used in surveys. Simulations succeed on large scales because gravity is simple and relentless, and because the relevant physics is dominated by collisionless dynamics. The Webb's statistics match surveys when initial fluctuations are nearly Gaussian and adiabatic, as predicted by simple inflationary scenarios. Halo mass functions and clustering broadly follow the standard model, from dwarf-scale halos to massive clusters. This is a major triumph because it links microkelvin CMB ripples to megaparsec structure, connecting the smallest measurable contrasts to the largest visible patterns. The hard part is the middle, where small-scale physics controls visible outcomes, and where the baryons refuse to behave politely. Stars form in dense, turbulent, magnetized gas that we cannot fully resolve, even in the best modern simulations. Supernovae and radiation inject energy into a multi-phase medium with strong cooling losses, so feedback can fizzle or explode depending on local conditions. Magnetic fields and cosmic rays add pressure and transport that are difficult to model from first principles, yet they can reshape winds and regulate star formation. Subgrid recipes compress unresolved physics into parameters, and those parameters steer galaxy demographics in ways that can look deceptively realistic. Change the coupling of feedback to gas, and disks thicken or survive, while bulges grow or remain small. Change cooling and mixing, and metals distribute differently through halos, altering how efficiently gas can radiate and collapse. The same initial conditions can yield different morphologies, star formation histories, and satellite populations, which is both a warning and a clue. This is why galaxy diversity remains a central challenge, not a cosmetic detail, because diversity is the observable face of hidden microphysics. Some galaxies quench early, others keep forming stars for billions of years, and the difference can hinge on environment or black hole activity. Dwarfs can be dark matter-dominated yet show bursty star formation and fragile gas reservoirs, as if they are repeatedly lit and extinguished. Scaling relations are tight despite messy histories, suggesting regulation we only partly understand, and raising the question of what sets the rules. Magnetic fields illustrate the scale-bridging problem in a concrete way, because they begin as whispers and end as architecture. Seed fields may arise from early plasma processes or stellar feedback, but their origin is uncertain and likely involves more than one channel. Dynamos amplify fields through turbulence and rotation, yet timing and saturation remain debated, especially in young galaxies. Fields then influence collapse, angular momentum transport, and outflows, feeding back into galaxy evolution and leaving signatures in polarized radio emission. Theoretical work also tests alternatives, because the standard model is strained by tensions, and tensions are where new ideas earn their keep. The Hubble constant discrepancy persists across methods, suggesting systematics or new physics that shifts the early or late expansion rate. Late time clustering appears lower than some predictions, hinting at altered growth or subtle observational biases in lensing and galaxy surveys. Possibilities include early dark energy, neutrino physics, or evolving dark energy behavior, each with distinct signatures that future data can separate. Transition. With tools and models in hand, we return to the stage itself. The expansion of the universe is not background. It is an active player that sets the conditions for every structure. Expansion cools the universe by redshifting photons and diluting matter, enabling atoms to form once temperatures fall below ionization thresholds. Cooling allows recombination, releasing the CMB and starting the Dark Ages, when the cosmos becomes transparent yet largely unlit. Expansion also sets the horizon scales that define what can communicate and equilibrate, limiting causal contact in the early universe. The early balance between expansion rate and gravity determines which perturbations can grow and which are erased by pressure and radiation. Yet expansion is also a tension, because it pulls space apart while gravity pulls matter together, and structure forms in the narrow gap between them. In the early universe, radiation pressure and rapid expansion resist collapse, smoothing baryons and delaying star formation. Dark matter helps by clumping without pressure, building potential wells first and deepening them through mergers. Baryons then fall in after decoupling, once cooling channels allow collapse to proceed, and shocks can radiate away their heat. Gravity is the local counterforce, and it explains why bound structures ignore expansion internally, even though they are embedded in expanding space. Galaxies, clusters, and solar systems are held by their own gravitational potentials, and their internal motions are set by virial equilibrium. Space expands between unbound regions, not inside virialized systems in any simple way, despite common metaphors. The boundary is not a wall, but a competition between binding energy and the changing cosmic background, an ongoing negotiation written in velocities and density contrasts. As dark energy dominates, the competition shifts again, and growth slows, because accelerated expansion stretches the web faster than gravity can knit it. Accelerated expansion reduces the rate at which new structure forms on large scales, even while existing halos continue to evolve internally. Voids expand faster, and the web's contrast increases even as overall growth stalls, sharpening the cosmic landscape. The far future becomes more isolated as distant galaxies slip beyond observable reach and the night sky grows quieter. This context reframes the entire narrative chain as a sequence of thresholds, each one triggered by temperature, density, and time. The early universe begins hot, dense, and nearly uniform, with tiny fluctuations that are small in amplitude but rich in consequences. Expansion cools it into nuclei, then atoms, then molecules, each step opening new pathways for chemistry and radiation. The CMB records the moment photons decouple and begin free travel, carrying a snapshot of acoustic waves frozen into temperature and polarization patterns. The dark ages follow, with neutral hydrogen and faint chemistry, and no new visible light beyond the fading afterglow. Dark matter halos grow, and baryons accumulate where gravity provides an address, gathering into denser pockets within the web. First stars ignite, ending the long night with ultraviolet light and heavy elements, and their radiation begins to carve ionized bubbles. Reionization reshapes the intergalactic medium and changes how small galaxies can form, because heated gas resists falling into shallow potential wells. Galaxies assemble within the cosmic web through accretion, mergers, and feedback regulation, and their shapes reflect how they gained and lost gas. Disks form where angular momentum is retained, and spheroids grow through mergers and instabilities that randomize stellar orbits. The Milky Way becomes one mature outcome, with a bar, spiral structure, satellites, and a massive dark halo that anchors its motion. Within its enriched gas, the solar system forms from a rotating disk of dust and gas, where grains stick, collide, and gradually build worlds. Planets emerge through accretion, migration, and impacts, and chemistry becomes increasingly complex as energy flows organize matter. Heavy elements forged in earlier stars become rocks, oceans, and atmospheres, and isotopic ratios preserve clues about ancient heating and mixing. Stable energy flows and long timescales allow biology to appear at least once, turning geochemistry into metabolism and information. The chain from microkelvin anisotropies to living cells becomes plausible, but it remains contingent, because small differences in timing and environment can redirect outcomes. Now we face the remaining mysteries directly, because the finale must be honest, and honesty is part of the scientific method. The deepest unknown is what happened at the earliest times, before our observational wall and before familiar physics is securely tested. Inflation explains several features, but its trigger, duration, and graceful exit remain uncertain, and competing models can fit the same broad data. We still do not know why initial conditions had the specific spectrum and amplitude that permit galaxies, rather than a universe too smooth to clump or too rough to remain stable. We also do not know what seeded structure in the most fundamental sense, even if we can describe the seeds mathematically. Quantum fluctuations stretched by inflation are a leading idea, but alternatives exist, and some leave subtle differences in phase correlations. Primordial non-Gaussianity constraints are strong, yet not definitive, because cosmic variance limits what one universe can reveal. A clean detection of primordial B-mode polarization would be a decisive clue, but foregrounds and systematics still complicate the search, and the signal is expected to be vanishingly faint. On the astrophysical side, we still struggle to predict galaxy diversity from first principles, because feedback is both essential and hard to compute. Feedback coupling in a clumpy medium remains uncertain, especially across phases where cold clouds, warm ionized gas, and hot plasma exchange mass. The roles of turbulence, magnetic fields, and cosmic rays are not fully constrained by observations, even though each can provide pressure and drive winds. Small-scale dark matter physics could also reshape halos and satellites, and current data do not close the case, leaving room for warmer, self-interacting, or otherwise modified scenarios. The stalemate can break only if new observations target the missing epochs and hidden components, and if they do so with enough redundancy to expose bias. 21-centimeter mapping can probe the Dark Ages and cosmic dawn directly, tracing neutral hydrogen before and during first light as absorption and emission patterns evolve. Next-generation CMB experiments can refine polarization and lensing, tightening early universe constraints and improving our map of matter integrated along the line of sight. Large surveys will map billions of galaxies, improving growth measurements and testing dark energy evolution, while also revealing rare objects that stress our models. New messengers widen the evidence base beyond light, and they change what is measurable because they travel differently and interact weakly. Gravitational waves provide distances and probe compact object populations across cosmic time, turning mergers into standard sirens with independent calibration. Neutrinos and cosmic rays trace extreme environments and feedback channels, pointing back to shocks, jets, and dense nuclear regions. Multi-messenger events connect engines to environments, linking microphysics to cosmological context, and letting us test models under conditions no laboratory can reproduce. Simulations will also change, but only if they become more predictive and less tuned, so that agreement is earned rather than adjusted. Higher resolution reduces reliance on subgrid recipes, but cannot eliminate them, because star formation and plasma processes span orders of magnitude. Better plasma and radiation modeling can constrain feedback and magnetic amplification, and improved numerical methods can reduce artificial mixing and diffusion. The goal is not a perfect universe in a computer, but a model that fails in informative ways, revealing which assumptions were doing the real work. The central question returns for the last time, now sharpened by evidence and bounded by ignorance, which is the honest boundary of knowledge. We can trace a plausible, evidence-backed pathway from near-uniform beginnings to the cosmic web, and we can test that pathway against multiple independent datasets. We can connect that web to galaxies, to the Milky Way, and to a planet that can ask questions, and we can explain many links with quantitative precision. But the deepest origin of the initial conditions remains open, and some key steps in structure formation remain only partially understood, especially where baryons become complex. We do not yet know what set the first seeds, or whether inflation is the full story or merely an effective description of a deeper mechanism. We do not yet know why galaxies regulate themselves so tightly, or which hidden physics shapes their diversity, from dwarf satellites to giant ellipticals. The universe gives us relics, and we are still learning how to read them and to recognize when we are projecting patterns onto noise. We end with a grounded kind of awe, because uncertainty is not a failure of science, and it is not a gap to be ashamed of. It is the engine that keeps observation and theory moving forward together, tightening constraints and forcing clearer questions. From almost featureless beginnings, tiny irregularities grew into stars, galaxies, and worlds through gravity and time. And the process left measurable traces at every stage. The story is unfinished, and that unfinished edge is where discovery begins. We began with a universe that looked almost perfectly smooth, a bright, opaque plasma where light could not yet travel freely. As expansion cooled that fog into atoms, the first molecules formed, gravity took over, and dark matter provided the hidden scaffolding where ordinary gas could finally gather. The cosmic microwave background became our earliest map, its micro-Kelvin modeling and acoustic patterns recording the initial blueprint, while later surveys traced that same pattern into filaments, halos, galaxies, and the star cities that forged heavy elements. From the long dark ages to the first stars and patchy rionization, we watched complexity ignite, then spread through feedback, mergers, and the restless circulation of gas, dust, and radiation. Up close, the Milky Way turned into a laboratory, its spiral shocks, chemical clocks, and Gaia-mapped collisions showing how cosmic history is written into stellar motions and starlight. And at the edge of knowing, we confronted the method itself, cosmology as forensic science, built from relic light, standard rulers, lensing, and simulations that succeed on the largest scales, yet strain under tensions in the Hubble constant, late-time clustering, and the messy physics of magnetized, turbulent baryons. Across every chapter, one theme kept returning, that the universe is not merely expanding, it is remembering, preserving early whispers in the CMB, then echoing them forward into the cosmic web, and eventually into worlds that can ask questions back. Yet even as the broad arc holds together, the missing pieces stand out in sharper relief. What lit inflation's fuse, what ended it, and why the seed pattern landed in the narrow range that allows galaxies to form at all. We still do not know what dark matter is, only that its gravity shaped the first wells, nor do we know whether primordial gravitational waves left a clean B-mode signature that could let us glimpse physics before last scattering. We do not fully know how magnetic fields were born, how quickly cosmic dynamos amplified them, or how reconnection and diffusion steer star formation across a multi-phase medium. And we cannot yet say whether today's cosmological tensions are measurement scars or the first cracks in a model that has carried us remarkably far. Still, the evidence chain is real, and it is astonishingly coherent when seen as one story. Tiny irregularities, perhaps quantum in origin, were stretched to cosmic sizes, then gravity amplified them while radiation resisted, and expansion set the tempo for every transition. When the universe became transparent, the CMB froze a snapshot of those seeds, and when matter finally cooled enough to collapse, the first stars turned hydrogen and helium into the heavier elements that make rocks, oceans, and cells possible. Galaxies did not appear as isolated islands, but as traffic in a vast network, shaped by mergers, fed by filaments, and regulated by feedback from stars and black holes. Our own home is not an exception to the pattern. It is one thread in it, assembled from recycled stardust, orbiting within a galaxy that still bears the scars of ancient collisions. If there is closure here, It is not the end of mystery, but the end of a false simplicity. The early universe was never truly nothing. It was a near uniform stage filled with energy, laws, and a faint, consequential texture. Those barely perceptible ripples, measured at 1 part in 100,000, were enough to grow everything we recognize, given time, gravity, and the quiet persistence of physics. In that sense, the symmetry did not so much break as it revealed itself, the way a perfectly still lake shows its depth only after the first wind touches the surface. So, what seeded the first structure, and what are we still missing in the story of how emptiness became a universe? We can now answer the middle of that question with confidence. Galaxies formed because tiny primordial irregularities were magnified by gravity, guided by dark matter, and paced by expansion, leaving fossils in relic light and cosmic structure. But the beginning of the question remains open, because the origin of those seeds, and the reason the universe began in just this delicately fertile state, still lies behind an observational curtain we are only starting to lift. Maybe the most honest conclusion is that the universe is not a solved equation. It is a continuing investigation, and every new instrument widens the boundary between what we know and what we can ask. If we find primordial B modes, or pin down the Hubble tension, or uncover dark matter's true nature, we will not erase the mystery. We will move it to a deeper layer, closer to the first cause. And if we learn how magnetic fields, turbulence, and feedback truly sculpt galaxies, we will better understand how complexity arises, not as an accident, but as a natural consequence of simple beginnings pushed through time. In the end, the most unsettling possibility is also the most beautiful one, that everything you have ever loved emerged from a nearly featureless universe because a faint pattern was there from the start, and because the cosmos had billions of years to let that pattern grow. The unexplained mysteries are not a failure of the story. They are the engine of it. Proof that the universe still has chapters it has not yet taught us to read. If you want to be part of that unfinished ending, follow the next maps as they arrive. CMB polarization, 21 centimeter echoes, gravitational waves, and the billion galaxy surveys that will test whether our best model is complete or merely the first draft. So what seeded the first structure? And what are we still missing in the story of how emptiness became a universe? We can now answer the middle of that question with confidence. Galaxies formed because tiny primordial irregularities were magnified by gravity, guided by dark matter, and paced by expansion, leaving fossils in relic light and cosmic structure. But the beginning of the question remains open, because the origin of those seeds, and the reason the universe began in just this delicately fertile state, still lies behind an observational curtain we are only starting to lift. In the end, the most unsettling possibility is also the most beautiful one, that everything you have ever loved emerged from a nearly featureless universe because a faint pattern was there from the start, and because the cosmos had billions of years to let that pattern grow. The unexplained mysteries are not a failure of the story. They are the engine of it, proof that the universe still has chapters it has not yet taught us to read. If you want to be part of that unfinished ending, follow the next maps as they arrive. CMB polarization, 21 centimeter echoes, gravitational waves, and the billion galaxy surveys that will test whether our best model is complete or merely the first draft.